362. Art. 22 GDPR. Automated individual decision-making, including profiling. 1. The data subject shall have the right not to be subject to a decision based solely on automated processing, including profiling, which produces legal effects concerning him or her or similarly significantly affects him or her. 2. Paragraph 1 shall not apply if the decision further text omitted here, GDPR 2018. Profiling, in GDPR, means any form of automated processing of personal data consisting of the use of personal data to evaluate certain personal aspects relating to a natural person. Thus, profiling should be construed as a subset of processing. Under two conditions, the processing is automated, and the processing is for the purposes of evaluation. Goodman and Flaxman 2017. Article 22, in the context of surrounding text and definitions. Restrict S. Automated individual decision-making, that is, algorithms that make decisions based on user-level predictors, which significantly affect users. The law also effectively create S. A right to explanation, whereby a user can ask for an explanation of an algorithmic decision that was made about them. Goodman and Flaxman 2017, 1. European law is European law, of course. But, nevertheless, GDPR is the result of deep consideration and analysis. It highlights the need for caution with use of personal data to produce decisions that affect people and a need for explanations of individual decisions that are made. Automated decision-making, ADM, using data about people as input and producing decisions that affect people as output, has been around for a very long time. For example, the Constitution of the United States requires 363. That there be a census every 10 years. The results of this census determine how many seats each state has in the House of Representatives, among other things. Processing data on this scale used to be a nightmare. Processing the 1880 census took 8 years, Roberts 2019, 100, in 1889. Kerman Hollerith received a patent for the art of compiling statistics. It was a patent for the punched card. A hole is thus punched corresponding to person, then a hole. According as person is a male or female, another recording. Whether native or foreign-born, another either white or colored. And c. Hollerith 1889. The data about each individual person was entered on a single card as punched holes. But then the data could be aggregated by running through the cards and using an electromechanical device to detect the relevant holes. The data also could be combined across categories. For example, were you to have an interest in white female carpenters, it was essentially trivial in principle to determine how many there were in a region or a state or, indeed, in the United States. Hollerith cards were taken up by wider businesses and commercial concerns, and the processing techniques led directly to the formation of IBM and the standard IBM 80-column punched card. Hollerith and his card won the 1889 Bureau of the Census competition to mechanize the process of conducting the census. The 1890 census was automated. Thus, there has been ADM for a while, maybe for 130 years. You can see the strengths and weaknesses of this original automation of the census. It makes viable a very difficult practical problem. There. 364. Should be few or no errors in the actual processing of the stacks of punched cards. Additionally, the actual processing is completely transparent and, in principle, could be inspected by anyone. but the data needs to be sound. If the data entry for an individual punches a hole for a farmer when the individual is actually a carpenter, garbage is part of the input and the results of that garbage and potentially can appear in the output as garbage out. Even worse if groups of people are not even included or properly represented in the census, there certainly could be bias or unfairness in what comes out. Nowadays, ADM has spread far and wide. Not all such decisions involve data about people as input, not all directly affect people as output. Not all involve machine learning. In fact, probably machine learning forms a relatively small, but increasing, part of ADM. After all, powerful machine learning has been available only for maybe 5 to 10 years. Here are some examples where machine learning may place a role in ADM. Autopilots on airplanes and similar technologies on ships, trains, and motor vehicles. Many decisions in the financial realm, such as investing, the identification of suspect financial transactions, credit card, or mortgage eligibility, and what interest rates those eligible are. In Title II, Medicine, identification of possible positive indicators of skin or breast cancer. The behaviors of industrial robots. 365. Military, robotics on the battlefield including unmanned systems and vehicles of various kinds, providing evidential input to sentencing decisions in criminal trials. Various decisions involving employment, e.g. interviews, promotions, remedial interventions, making suitable chess moves to be a companionable opponent or to be a tutor of the appropriate level, and many, many more. Some of these types of decision-making involve partnerships with humans. Humans may have overrides, may make the final choice or decision, etc. The strengths and weaknesses here are similar to those of the original census automation. But there are differences. Many of the systems, or their intellectual aspects, are owned by private companies, sometimes very large companies. A result of this is that often the systems are proprietary and are trade secrets. With this, transparency can disappear. Outsiders may have no way of being assured that the actual processing is sound. When it comes to machine learning and large language models, for example, even the companies and their researchers can be in a position of not really knowing how their complex systems work, if, indeed, they do work. In this case, transparency is not being hidden by companies, it is simply not available. A factor here is that large language models, for example, are so expensive to establish that only the largest companies or the government have the resources to create them and do research with them. Universities do not have the money to become involved directly. In many fields, one thinks of 366 universities as being able to be qualified and intelligent, honest outside agents. But this is not true for advanced machine learning. The universities cannot participate at all at a core level. Then there is an important difference regarding the data. In immigration controls in airports and similar, the government uses machine learning face recognition technology to scan the incoming crowds for persons of interest. The government does not seek anyone's approval or consent to do this. This is similar to gathering the original census data back in 1890. There is a social contract between members of the community or society that gives implicit consent from members of that society to their government to carry out various governmental tasks and procedures. But the situation with private companies is different. If you walked into a shopping mall and the mall scans Your face, without your knowledge or informed consent, how is this right or ethically appropriate? In sum, attention needs to be paid to transparency and the uses of data. There is a lack of insight, a lack of transparency, and often a lack of informed consent. Putting this right perhaps falls to many parties, to the creators of the systems, to the makers of laws, to educators, and to the citizenry at large. Several countries, or groups of countries, do have laws. For example, as we have seen, there is the European GDPR. The USA does not have a relevant all-encompassing laws. Librarians certainly can play a role. Ridley and Pollock-Potts 2021a. Assume so, what can they do? The librarians can become knowledgeable themselves. The Masters of Library and Information Science, MLIS, degree, which is the Union Card for advancement in professional librarianship, might include a courses in the wider aspects of machine learning. None do, 2023, in the USA. 367. Libraries, as institutions, can offer opportunities to their staff to increase their knowledge in this area. This might include courses, workshops, hands-on sessions. Then the librarians might be alert to inform their patrons about surveillance, consent, privacy, automatic decision-making, etc. 13.9 Explainable Artificial Intelligence, XAI. There is a research field, Explainable Artificial Intelligence, XAI, that has direct relevance to automated decision-making. Exposure to the ideas of Explainable Artificial Intelligence, XAI, is of benefit to folk trying to educate others about machine learning. Explainable AI is machine learning that has the property of being easily understood by humans, Wikipedia 2023e. What ML systems can tell us is that certain observable features, feature data, are connected with other observable labels, label data, for example. That being written by J.K. Rowling is correlated with being a popular book. Sometimes an ML system will tell us the labels, the predictions, without being able to tell us of the specific features that it used in its inference or calculation. In these cases, the ML system is a black box. You give it a book, the features of a book, and it will tell you if the book will be popular. It is an oracle. Henceforward, here, as an abbreviation, Oracle MLs. At this point, we will take a brief detour into two areas of philosophy, the philosophy of knowledge, epistemology, and the philosophy of understanding and explanation. 368. We want to distinguish knowledge from right opinion. This is a distinction from Plato's Meno, amplified by John Stuart Mill's work on freedom of speech, Plato 380 AD, Mill 1869. Nowadays, right opinion would probably be more usually described as being true belief. Plato defined knowledge as having three components. Knowledge needs to be true. It needs to be believed. It needs to be justified. An oracle ML might provide right opinion, but it does not give knowledge. For knowledge, the knower has to have evidence and be able to provide a reasoned defense, or explanation, or justification of the known. In brief, the knower has to be able to give the reasons why. Socrates argued, true opinions, while they abide with us, they are beautiful and fruitful, but they run away out of the human soul and do not remain long, and therefore they are not of much value until they are fastened by the tie of the cause. When they are bound, they have the nature of knowledge, and they are abiding. And this is why knowledge is more honorable and excellent than true opinion, because fastened by a chain, Plato 380 AD, 98. An oracle does not give knowledge. It does not give causes. Then, what, in this context, is understanding? A simple but plausible answer given by contemporary philosophers of science is as follows: to understand a phenomenon is to grasp how the phenomenon is caused. Strevens. 2013. 369. The phenomena of interest here is how the successful ML systems produce the correct predictions that they do. To understand, we need to know the causes at work. With oracles, the causes are exactly what we do not have. Hence, to address these considerations, there is the existence of the research field Explainable AI, XAI, with its own techniques and methods. Space does not permit extended discussion here of XAI. There are actually two causal problems with oracles. There is the problem of specific predictions, understanding why a specific prediction has been made in a particular case, and there is the problem of understanding how a given oracle works as a whole inside its black box. An example of the first problem is when a radiologist works in partnership with an ML system to assess a patient and to diagnose possible cancer. The radiologist and the patient need to know the basis of, or evidence for, the ML system's prediction. The reason for that need is that knowledge is better than right opinion. Knowledge is better for trust, ethics, respect for human beings, decision-making, regulatory and legal requirements, etc. An example of the second problem is that the designers or programmers of the radiology image diagnosis system should understand how it works. That would help them going forward to assess and improve the system. Strevens 2013. Elsewhere, we do negotiate our lives using correlations, right opinions. The farmer puts fertilizer on crops, we take aspirin for headaches, and a majority of U.S. avoid smoking for health reasons. Some of these connections are undoubtedly causal, but we usually do not know of the details of the causality. Often, this is the best we can do. The phenomena, the laws, if 370. There are any, the initial conditions, and the interactions of these, are all intertwined and complex. Often, they are also probabilistic. Basically, the systems are close to being black boxes. If XAI can do as well as agriculture and medical science, that might be good enough. 13.10 Annotated readings for Chapter 12. Druga, Stefania, Sarah T. Gavu, Ishli Keith, and Tammy Cho. Inclusive AI Literacy for Kids Around the World. In Proceedings of FabLearn 2019, 104-11. FL 2019. New York, New York, USA, Association for Computing Machinery, 2019. https://doi.org/10.1145/3311890.3311904. Druga et al. 2019 b. Gesser, Avi, Robert Maddox, Anna Gressel, Manisu, Samuel J. Alleman, and Andres S. Gutierrez. New Automated Decision-Making Laws, 4 Tips for Compliance. Debevoise Data Blog, 2022. https://www.debevoise-blog.com/2022/06/25/new-automated-decision-making-laws-for-compliance/. Gesser et al. 2022. Goodman, Bryce, and Seth Flaxman. European Union Regulations on Algorithmic Decision-Making and a Right to Explanation. AI Magazine 38, Number 3, 2017. 50-57. https://doi.org/10.1609/imag.b38i3.2741. Goodman and Flaxman. 2017. Middlestead, Matthew G. Artificial Intelligence, An Introduction for Policymakers. Mercatus Center, 2023. https://www.mercatus.org/research/research papers/artificial-intelligence-intro-for-policymakers. Middlestead, 2023. Nori, Harsha, Samuel Jenkins, Paul Koch, and Rich Caruana. Interpret ML. C++. 2019. Reprint, Interpret ML, 2023. https://github.com/interpretml/interpret. Noriyiti. Al, 2019, 2023. Pritchard, Duncan, John Turry, and J. Adam Carter. The Value of Knowledge. In the Stanford Encyclopedia of Philosophy, edited by Edward N. Zalta and Yuri Nodelman, Fall 2022. Metaphysics Research Lab, Stanford University, 2022. Pritchard, Turry, and Carter 2022. https://plato.stanford.edu/archive/fall2022/entries/knowledge-value/. This is a valuable resource on considerations of knowledge versus right opinion. Ridley, Michael, and Danica Pollock-Potts. Algorithmic Literacy and the Role for Libraries. Information Technology in Libraries 40, Number 2, 2021. https://doi.org/10.6017/ital.b40i2.12963. Ridley and Pollock-Potts 2021b. 371. Stanford HI. Generative AI, Perspectives from Stanford HAI, 2023. https://hai.stanford.edu/site/default/file/2023-03/gernative_ai_perspectives.pdf. Stanford HAI 2023b. These are Perspectives from Stanford Leaders in Medicine, Science, Engineering, Humanities, and the Social Sciences on how generative AI might affect their fields and our world. Solmont, Elizabeth Petitzas, and Jeremy R. Cooperstock. Can you teach me to machine learn? In proceedings of the 50th ACM Technical Symposium on Computer Science Education, 948-54. 619. New York, USA. Association for Computing Machinery, 2019. https://doi.org/10.1145/3287324.3287392. Solmont, Petitzas, and Cooperstock. 2019. 372. Chapter 14, Librarians as Managers. 14.1 Coming on Board. Libraries need management, and many librarians have management duties. Of course, they are usually assisted in these duties by computers and general library automation. The use of AI or ML in this setting would be a step further. Amanda Wheatley and Sandy Herviews have published an environmental scan of the use of AI in academic libraries, Wheatley and Herview 2019. Their appraisal is bleak. Here are some quotations from the Wheatley and Herview paper, offered without comment or judgment. What is perhaps the library's best-kept secret has been its slow uptake on automation and digital technologies. On the possibility of libraries being run by machines, this unsettling reality should have awoken librarians. Instead, the Profession reacted as it did to most technological revolutions. It waited. In fact, it is still waiting. The absence of scholarly research on AI-related technologies in libraries is not to be unexpected. Libraries have suffered from issues on the adoption of digital technologies and a general resistance to change throughout the 20th and 21st centuries. The progression of industrial and office automation paved the way for libraries to adopt similar technology, yet this adoption was always years behind the current trends. 373. The current state of artificial intelligence in academic libraries has proven to be nearly non-existent. Separately from this environmental scan, there are literature reviews that range wider than academic libraries. Rajesh Das and Muhammad Islam, in their systematic literature review of the application of AI and ML in libraries, identify in the publications the following 10 themes: R. K. Das and Islam 2021. Collection building and management. Processing in libraries. Circulation and user studies. Reference service. Library administration. Library customization and retrieval. Research and scholarship. Service quality and innovation. Intelligent agents for information search and retrieval. Study on implementation and existing technologies and solution. Their review is backward-looking, of necessity. It is considering what has been done prior to 2020 and what AI and ML techniques were used to do it. There is also Andrew Cox, Stephen Pinfield, and Sophie Rutters. The Intelligent Library, thought leaders' views on the likely impact of artificial intelligence on academic libraries, Cox, Pinfield, and Rutter 2019. This 374 does have valuable content. Its editorial summary is excellent. But it is old. And it is not clear how well informed the 33 thought leaders were around 2018. One of them did not know what artificial intelligence was, and none of them knew about large language models, nor did the rest of us. IFLA is the International Federation of Library Associations and Institutions. It styles itself as the global voice of the library and information profession. Its 2022 Trend Report update has no mention of artificial intelligence or machine learning, Al-Badi et al. 2023. IFLA does have its earlier statement on libraries and artificial intelligence, which is very good, IFLA 2020. Barbara Wood and David Evans write in their paper Librarians: Perceptions of Artificial Intelligence and Its Potential Impact on the Profession. The results of our survey point to an overwhelming sense of complacency among librarians in regard to the transformative/disruptive effects of this technology. For the past 35 years, academic libraries have successfully embraced computerization. Why is it that, at this time, we have our heads in the sand? We liken it to the climate change debate. The data is there, but we choose to ignore it. Wood and Evans 2018. For us, it is worthwhile for us to consider aspects of these themes which we have not considered elsewhere. In Chapter 10, the following topics were mentioned: workflow and improving service. 375. Optimize the use of space, and, indeed, other resources. Robots. Mimicking librarian experts' behaviors. We are interested specifically in machine learning and artificial intelligence, not in plain automation. We are using the R. K. Das and Islam 2021 as the skeleton for this. 14.2 Data and Analyses. There will be data on resources, processes, user behavior, and more. From these, there can be Predictive analytics. This identifies past usage patterns and trends as input to predict demand and need. It could be looking at many types of data as input: demographics, time of day, time of year, e.g. exams, summer breaks. With machine learning, it does not really matter how rich or apparently irrelevant the types of data. After training, anything known that is not connected with the correlations will just be given weight 0, i.e. discounted. User behavior analytics. This is data on what the patrons are doing, either individually or collectively. Attention needs to be given here to privacy or informed consent. Anonymous data, for example, on which books are frequently checked out, can help with decisions on which books to keep physically in the stacks and which to store elsewhere, perhaps off-site. In contrast, recommendation systems will 376 work better with information tied to patrons individually that still can be kept anonymous. Learning analytics. In cases where libraries are serving students, faculty, and research, there can be data on what resources the patrons use and how they use them for the purposes of teaching and learning. In turn, this can be used to improve the process of education. There is a large and burgeoning field: artificial intelligence in education. AI'd. See, for example, Stanford HAI 2023 A. Librarianship will have a role in this. That role will extend to school libraries and public libraries. 14.3 Evidence-based librarianship. When making decisions, evidence-based practices encourage the use of the best available evidence in conjunction with expertise and attention to values. Wikipedia 2023 D. This approach tends to downplay tradition, especially when no one knows why the tradition is as it is. There is evidence-based library in information practice, IBLIP, with supporting books, research articles, and a journal, for example, Jorland 2011. University of Alberta Library 2023. Maybe now is its time. There is now plenty of data, and ML can analyze a quantity of it in a way that no human can. Of course, the management and administration of libraries used any amount of data prior to the advent of a blip. But now there is much more data and the existence of ML that can interact with that data intelligently. As mentioned many times, ML can deal with volume in a way that collective human resources cannot. 377. 14.4 Data-driven decision-making. 14.4.1 Collection building and management. ML can analyze the collection and its uses. Predictive analytics can be used as part input on decisions on which materials to purchase, keep in the collection, or weed or discard. It can help with resource allocation. The analysis would take input from availability of materials in other libraries, or the needs of the library's users. See, Litzy and Malden 2018. 14.4.2 Circulation and User Studies. Service, recommendation, personalization, and AIED all have relevance. Here, ML together with the data analytics mentioned earlier have the potential to affect improvements. 14.4.3 Processing in libraries. AI can help with many of the processes that are part of librarianship. Most of these have been mentioned earlier in this text, including cataloging, classification, acquisition, archiving, digitization, transcription, translation, indexing, and summarization. 378. 14.4.4 Research and Scholarship. The view here is that shortly the information discovery techniques and tools are going to be far superior to the ones we have today. We have amplified on this thesis throughout this text. What managers should do is to support the use of these tools. 14.4.5 Service Quality. There will be improved metrics on most aspects of service. Being able to measure how good service is does not of itself guarantee good service. But whenever insights or innovations come to the fore, it is good to know whether they actually do make service better. 14.5 Acquiring the appropriate AI tools. The managers can acquire the relevant AI tools. IFLA makes a suggestion that would kill another bird with that stone. Libraries can also support ethical AI research and development by their procurement choices, purchasing AI technologies which abide by ethical standards of privacy and inclusivity. This would both reaffirm the trust of users in libraries and send a message to the AI research field by increasing the demand for ethical AI technologies. IFLA 2020-2. 379. 14.6 Analysts and staff. There is a shortage of skills and awareness. The demands of responding to such changes may reveal a significant skills gap in the sector. We know there is already strong demand in the economy for data scientists for data analysis and visualization. Perhaps some librarians will be required to develop these skills, or at least awareness of different techniques and how they need to be supported. These demands are a challenge because they prompt librarians to learn more about IT and quantitative data analysis, including statistics. In a relatively low-paid sector, we may be unlikely to attract people with stronger STEM backgrounds to the profession, while those in the profession are typically from an arts background. More optimistically, we can say there will also be a need for librarians as data curators to take on new data. Cox, Pinfield, and Rudder 2019-17. Foundation models have given us all a break here. You do not have to be a programmer or a mathematician to use, develop, or configure LLMs. You can even be from an arts background. So-called prompt engineering makes many things possible. We will look further into that in Appendix B. 14.7 Fear of AI. Within the library profession there does seem to be a fear of AI, as evidence, see, for example, Cox, Pinfield, and Rudder 2019, Ex Libris. 2019. 380. Ex Libris invites us librarians to be liberty leading the people, Wikipedia. 2023 H. Embracing AI not as users, but as active players to fight the risks of bias, misuse, and discrimination if libraries take an active role in the implementation of artificial intelligence applications in the information management landscape, then they can help programmers find the best data for their algorithms. Once they assume the leading role, librarians can be co-creators of an intelligent information system that respects the sources, engages critical inquiry, fosters imagination, and supports human learning and knowledge creation, according to Catherine Nicole Coleman. AI solutions can also facilitate both more process transparency and greater data control, with libraries able to safeguard their most important principles and maintain trust, neutrality, freedom of expression, mindful media consumption, and equal access to information, while promoting digital inclusion and data privacy. Advocacy should not be directed at maintaining traditional librarianship, but in influencing the development of the emerging information systems. Ex Libris 2019. 14.8 Annotated readings for Chapter 14. Gale, part of Signage Group. Library Marketing, Improve Outreach with Gale. Analytics, 2023, https://www.gale.com/databases/gale-analytics. Gale, part of Senyage Group 2023. Litzy, Ryan, and Weston Malden. Knowing what the patron wants, using predictive analytics to transform library decision-making. The Journal of Academic Librarianship 44, Number 1, 2018 140-44. https://doi.org/10.1016/j.acalabi.2017.09.004. Litzy and Malden 2018, this is old now, before LLMs. One commentator describes that it seems like a dystopian vision that thinks it's a utopian vision. 381. Chapter 15, Librarians as Astronauts. 15.1 Astronaut Training. Well, you are in a good place to do creative work with foundation models. You do not need to know anything about machine learning or computer programming. You do not even have to have any domain knowledge about the area you are going to work in, which we are assuming here to be librarianship. The foundation model you use will have all the knowledge that is required. Your role is to ask it in ordinary natural language, to prompt it to do whatever you are looking for. Over the past 20 years or so, many librarians have become absolute experts at using search engines, say Google search. Now there are new kids on the block. Foundation models, large language models, or large multimodal models. It would not be a bad thing at all for many librarians to become absolute experts at LLMs or LMMs. 15.2 Why should you learn how to do it? Gives you understanding. Allows you to teach others. Allows you to produce apps. Allows you to work with ML professionals. 382. 15.3 What are the real creative possibilities? This is hard to know, stating the obvious. 3 areas where modern machine learning might have a distinction advantage over the incumbents in librarianship or in information curation and provision are data visualization, chatbots, and information discovery, including text data mining. Data science, making sense of data, is important. Having the right representation of the data is often critical to understanding that data and seeing how to reason with it. The key point was made by Jill Larkin and Herbert Simon in their paper Why a Diagram is, sometimes, worth 10,000 words. They suggest that informational equivalence should be distinguished from computational equivalence, Larkin and Simon 1987. The distinction can be explained by means of an illustration. Donald Norman drew attention to a famous example of 2 gains. Norman 1993. In the first, you and your opponent take turns in choosing and selecting single, previously untaken, numbers in the range 1, 9, and the winner of the game is the first person who has 3 numbers that sum to 15. So you try both to get numbers that sum to 15 and also to prevent your opponent from getting such numbers. In the second, you play tic-tac-toe, or noughts and crosses. 383. Now, the first game we would find awkward and might lose from time to time, until we devised a suitable representational scheme. The second is trivial, and an attentive adult would never lose a game. But the 2 games are the same. They are different representations of the same game. If the numbers are laid out as though they were on a tic-tac-toe board, 618, 753, 294, then the problem of finding 3 numbers that sum to 15 is exactly that of finding 3 in a vertical, horizontal, or diagonal line. Any information as to the board state or to the number selected is exactly intertranslatable back and forth between tic-tac-toe. Representation and number selected representation. There is information. Equivalence. But humans can manipulate and compute with one representation much more easily than the other. And, interestingly enough, a computer or a computer program would be more at home with the numeric representation as opposed to the two-dimensional board representation. Information opens up different possibilities for an agent depending on how it is represented. This is matter of the manipulations, operations, and computations that the depiction facilitates. A good collection of historical depictions of statistical data can be found in Michael Friendly's gallery of 384. Data Visualization, Friendly 2007. Machine learning may well be able to learn the best ways to represent data. Let us sketch some territories here. Insofar as this concerns diagrams, as it would for education and for research by humans, the area of interest is cognitive psychology and heuristics. Insofar as it concerns computer processing, it would be a matter of data structures and algorithms, parts of computer science. Librarians may be fine with either of these, but they are a little outside librarians' bailiwick. Chatbots have been discussed extensively in this text. Certainly, chatbots in libraries represent an opportunity, possibly even a research opportunity. But chatbots for the purpose of service are going to be everywhere. It may be hard for librarian developers to keep themselves clear of the development stampede. Information discovery and text data mining are both gifts to librarians. Librarians know from text. We will amplify shortly on one aspect of this possibility. 15.4 Sitting in your tin can. If you are going to sit in your tin can, you could think about how ML might provide new ways to interact with library resources. You could think about interactive games and simulations that might help with access or with AI literacy. You could think about many things. 385. 15.5 Exploring World 3. 15.5.1 Undiscovered Public Knowledge, UPK. In 1986, Don Swanson wrote as the abstract to his paper Undiscovered Public Knowledge. Knowledge can be public, yet undiscovered, if independently created fragments are logically related but never retrieved, brought together, and interpreted. Information retrieval, although essential for assembling such fragments, is always problematic. The search process, like a scientific theory, can be criticized and improved, but can never be verified as capable of retrieving all information relevant to a problem or theory. This essential incompleteness of search and retrieval therefore makes possible and plausible the existence of undiscovered public knowledge. 3 examples intended to throw light on the logic of undiscovered knowledge are constructed and analyzed. The argument is developed within the framework of a Popperian or critical approach within science and on Popper's distinction between subjective and objective knowledge, the distinction between World 2 and World 3. Swanson, 1986. The referenced work of Karl Popper can be explained thus. Popper had introduced in the idea of 3 worlds: World 1, the physical world; World 2, the mental world; and World 3, the world of objective contents of thought, especially of scientific and poetic thoughts and of works of art. World 3, objective knowledge, contains the contents of books and libraries, not the physical books, World 1, nor the mental ideas conjured. 386. Up by the books, World 2, but the contents of the books understood as the objective assertions they make. See epistemology without a knowing. Subject, Popper 1968. World 3 objects can stand in logical relations one to another. One book may contain the assertion Leda is a swan. Another book may contain the assertion all swans are white. Those two books, together, considered as a combined whole, entail the consequence that Leda is white. Swanson instantiated and generalized this in the following way. Suppose some recorded research tells that process A causes effect B and some entirely different recorded research tells that B causes effect C. Then A causes C, and this, perhaps hitherto unknown, relationship can be discovered by looking at the recorded research. This is an example of undiscovered public knowledge, UPK. A real scientific example that Swanson offered from 1986 is that it was known as recorded objective knowledge that A. Fish oil reduces platelet clumping, B. and reduced platelet clumping is, C. of benefit to patients with Raynaud's disease. But it was not known as objective knowledge, i.e. published anywhere as recorded knowledge that A. Fish oil can be, C. of benefit to patients with Raynaud's disease. That relationship can be discovered without entering a laboratory. It can be discovered without leaving a library. Usually, different assertions and findings need to be assembled across documents to create a new coherent assertion, much as different pieces of a puzzle are assembled to create a single picture. Smallheiser 2017, 3. We should keep in mind here that all knowledge is fallible and conjectural, so that when we appear to discover that fish oil helps with Raynaud's disease, we are discovering a new conjecture that apparently no one had 387 proposed earlier, and that conjecture would need testing. If its components had been thoroughly tested and were reliable, it may be that further testing could be minimal. That would depend in part on what the practical consequences would be of trusting the hypothesis. In the case of medical treatments and drugs, there are established protocols. It may be that the apparent conjecture from UPK had been known and discovered earlier. Researchers looking for treatments for Raynaud's disease may have had hundreds of conjectures as to what might be suitable, and their problem might have been how to spend their time and money. In this case, the ABC example given above screams loudly, try fish oil. UPK is still valuable. There are other kinds of UPK, Smallheiser 2017. There can be publications that no one currently reads. These may be publications in truly obscure journals or in outlets that retrieval systems have trouble in finding, perhaps due to poor indexing or metadata. Investigators in these areas often talk of one-node or two-node searches or of open or closed searches. If the search starts with process A and is trying to find anything it relates to, that would be a one-node or open search. If the search starts with two processes A and C and is trying to find a B that connects them, that would be a two-node or closed search. Don Swanson was a librarian. More strictly, he rose to being dean of the Graduate Library School of the University of Chicago. 388. 15.5.2 Literature-based discovery, text-based informatics. The seminal work of Don Swanson has been generalized and developed to form literature-based discovery, sometimes called text-based informatics. This is used widely in bioinformatics and medical informatics. See, for example, Crichton et al. 2020, Keatley 2023, Morrow 2023, Sebastian, Sue, and Oramate 2017, the Lacaratin, Faulkner, and Adapada 2020, Wikipedia 2023 A consideration of importance to us is that literature-based discovery until about 2020 used what we now would regard as being primitive bibliometric tools. Computers were used, and Google-style searches. It used authors, titles, keywords, subject headings, etc. But 2023 machine learning, especially LLMs, open up new possibilities. No doubt, UPK researchers are onto LLMs already. But the target domain is vast, every book in every library. There are opportunities for all. 15.5.3 A message to librarian astronauts. The growth of scientific knowledge is usually thought of in terms of wresting new discoveries from the physical world, World 1. Admittedly a world that offers unlimited opportunity for discovery. But it should be of interest to librarians to notice that World 3 also qualifies as an endless frontier and to understand how and why this is so. Swanson 1986, 117. 389. 15.6 Annotated readings for Chapter 15. Smallheiser, Neil are Rediscovering Don Swanson, The Past, Present and Future of Literature-Based Discovery. Journal of Data and Information Science. Warsaw, Poland, 2, number 4, 2017 43-64, https://doi.org/10.15/JDS-2017-0019, Smallheiser 2017. For here am I sitting in my tin can, far above the world. Planet Earth is blue, and there is nothing I can do. David Bowie. Space Oddity. 390. Appendix A, some theoretical background to librarianship. 8.1 Concepts, classification, taxonomies, and items. A central component of classification is concepts, and a whole collection of concepts, being used at once, amount to a taxonomy or conceptual scheme, or classification scheme. A concept has intension, meaning, and extension, which is the collection, or class, or set, of those items, or individuals, or things, in the world that fall under it, or are instances of it. Concepts will usually have labels, i.e. words, or names, that identify them. Some concepts can have two or more different labels. Such labels would be synonyms, e.g. attorney and lawyer. Some labels can label two different concepts. Such labels would be homographs, e.g. bank, of river, and bank, financial institution. There is a general looseness of terminology in classification areas. The terms concept, class, set, category, and probably other terms can get used interchangeably. We will go with the flow on this, for example, often using class or set for concept. A taxonomy, unless it is a simple list or dictionary, will always have at least one class which is a subclass of another class. Then the overall structure of the scheme might be a hierarchy, a polyhierarchy, a directed acyclic graph, a tree, a forest of trees, or some other graph theoretic structure. See Frick 2012. 391. At point 2 Controlled vocabularies and thesauri. In many settings, librarianship will use controlled vocabularies, CVs. A controlled vocabulary is collection of words, or terms, where the words are controlled, they have a fixed and definite form. As to the value of CVs, Elaine Spinonius writes, perhaps as near as one can come to generalization about the value of a CV is simply to say where precision and recall are important. Retrieval objectives, then a CV of some kind is mandated. Svenonius 2003, 837. There are more detailed explanations of CVs and their value in Frick. 2012, Harpring 2020, ANSI/NISO 2010, Zing 2005. CVs are still of value. In the age of computers and machine learning, as they provide a standard way to describe concepts and their relationships and a standard interface between different systems. The simplest CVs amount to little more than lists of terms. CVs used for indexing and metadata, e.g. subject classification, tend to be more sophisticated than this. They have a structure in the background, with links or connections between some terms. As an example, the Library of Congress subjects headings, LCSH, is a controlled vocabulary. LCSH has hundreds of thousands of terms in it, and it took 100 years or more to build. It is probably the biggest and most elaborate CV ever made. Its size and maturity are not the only points of interest. It also relates broader 392 and narrower terms, and it suggests preferred terms in the case of synonyms. Indexes typically use CVs. Each hierarchy in an index CV is a tree. But the index as a whole is not a single tree. There is not one single term at the top, with every other term being a subterm of it. Rather, there are several different trees. The structure is that of a forest. For example, the mesh subject headings are in 16 different trees. As an illustration, here are 6 of them: anatomy, organisms, diseases, chemicals and drugs, analytical, diagnostic and therapeutic techniques, and equipment, psychiatry and psychology. Thesauri are controlled vocabularies with relations provided between broader and narrower words or terms. However, some extant controlled vocabularies themselves have broader and narrow terms, e.g. the aforementioned LCSH. If this practice is acceptable, thesauri can be much the same as controlled vocabularies. A few words are in order about the nature of the lengths or relations between the broader and narrower terms. International standards for thesauri distinguish 3 possibilities here: subclass, instance, and part. NC/ISO 2010. Whales are a subclass of mammals. Moby Dick is an instance of a whale. A blowhole is part of a whale. So, an imaginary CV 393 might contain mammal, narrower term, whale, whale, narrower term Moby Dick, and whale, narrower term, blowhole, whale. The first relation would be subclass, sometimes called generic, the second instance, and a third partitive. The first 2 relations can come under the general approach of taxonomies. The third, addressing parts, is usually considered to be mereology, which is the study of parts and wholes. We will usually assume that the collection of top-level terms in a thesaurus, those that are not narrower terms of other broader terms, could be printed, displayed, or written out in alphabetical order. There is a small wrinkle here. Just what alphabetical order amounts to is a question. 2. Give an example. For a telephone directory, should Newark come before New York or after it? Where should numbers go? Where should foreign words go? Where should abbreviations go? The practice here is known as the filing order, and it is a matter of several decisions or conventions, which we will not go into. Point 3. Ontologies and ontological vocabularies. An ontology identifies what exists in a certain domain or area, i.e. the individuals, the properties, the classes, etc. As examples, a medical setting might have an ontology with doctors, patients, medicines, bacteria, etc. in it. A soccer game might have players, teams, balls, referees, pitches, and like. A library might have patrons, librarians, books, desks, reading rooms, and similar items. Computer scientists use ontologies as a guide to the requisite data structures needed for their programs. Librarianship is not really interested in ontologies as such, but it is interested in the words or 394 terms that are used. An ontology will have terms or words associated with the items that appear. So, for example, in a soccer ontology, pitch, field, and paddock are near synonyms for the surface on which the game is played. Such terms could be built into a controlled vocabulary, with pitch being the preferred term and field and paddock being lead-in terms. A thesaurus could also easily be used here, e.g. with soccer complex, having pitch as a narrower term. Ontologies themselves, or what we might call ontological vocabularies, could also be used. For example, libraries lend books, or, perhaps, libraries issue books. We can make one of these forms a preferred form and record in the ontological vocabulary that libraries lend books. Thus, ontological vocabularies, insofar as they provide relationships between words or terms, are a more general case than thesauri. 4. Example, consider, in a medical setting, the relationships is a symptom of, may be treated by, a relevant ontological vocabulary might have preferred terms for headache, fever, influenza, and aspirin, and also such relationships as headache may be treated by aspirin. If these possibilities are thought of in a graph-theoretic sense, a thesaurus links narrower terms to broader terms, and often the structure of this will amount to a tree, i.e. there is a root, and parent nodes can have many children, but each child can have only one parent. Some thesauri, for example the LCSH, permit some terms to have more than one broader term, i.e. a child node might have more than one parent node, in which case the structure would be a directed acyclic graph, DAG. In an ontological vocabulary, any node might possibly be linked to any other node. This 395 would amount to a general graph, i.e. a web of nodes and links. Roughly. Then, an ontology is a generalization of a taxonomy, and an ontological vocabulary is a generalization of a thesaurus. A point 4 objective, intersubjective, and subjective. These three terms are selectors among knowledge, or among candidates for knowledge. When an art historian describes a painting as being in the shape or proportions of a golden rectangle, she is picking out a property of the painting. She is making a perfectly objective ascription about the external world. She can be wrong, of course. There can be some mistake with her eyes or means of measurement. Nevertheless, right or wrong, she is aiming to be objective. Moving on, suppose her aesthetic is that of neoclassicism, to the exclusion of all else. She may describe a painting by Jacques-Louis David as being a good painting. That would be an intersubjective judgment. There are plenty of other neoclassicists, and they would have the same view. But neoclassicism itself is not part of the external world, it is an aspect of a certain kind of culture. Finally, there is the rest of us who know nothing about art but know what we like. Expressions of what we like would be subjective. Taxonomies also can be objective, intersubjective, or subjective. Objective schemes are the province of science and mathematics. Classifying matter into atoms, elements, compounds, and mixtures, or classifying the numbers into integers, reals, or rational numbers, or classifying parts of the biological world into genus and species are all objective schemes. As noted earlier, our knowledge of the objective is fallible, scientists or 396. Mathematicians can be mistaken, and hopefully they can correct the errors. Intersubjective schemes arise in a context of society, culture, politics, religion, myths, and the law. A good example is the nursing interventions classification, NIC. It is a comprehensive, research-based, standardized classification of interventions that nurses perform. It is useful for clinical documentation, communication of care across settings, integration of data across systems and settings, effectiveness, research, productivity measurement, competency evaluation, reimbursement, and curricular design. The 565 interventions in NIC, 7th edition, are grouped into 30 classes and 7 domains for ease of use. The 7 domains are physiological, basic, physiological, complex, behavioral, safety, family, health system, and community. Each intervention has a unique number, code. The classification is continually updated, with an ongoing process for feedback and review. In the back of the book, there are instructions for how users can submit suggestions for modifications to existing interventions were proposed. A new intervention, Butcher et al. 2018. This is not a description of the external world. This is not intended to tell us how the world is built. The continual updating is a bit of giveaway on this. It is not objective, in our sense of objective. Rather, it is a convenient fiction. Or, as some might say, it is a social construction. However, nurses, doctors, insurance companies, etc., all respect and use this fiction. It is intersubjective. It is artifact they all agree on and use. As to the final category of pure subjective classification, that, for example, is how you and I separately organize our clothes in our wardrobes. Most classification schemes in information organization are intersubjective, but some have components that supervene on objective. 397. Classifications. For example, schemes for classification of resources on science or mathematics, e.g. books and research papers, would typically partially follow objective classifications that the scientists or mathematicians use. A 0.5 emotive and descriptive content. Going back to the art historian describing a painting as being in the shape or proportions of a golden rectangle. Being golden rectangular as a property is not something that is either good or bad, and it is not something that she wants to recommend to you or to warn you away from. It is just a plain description. Golden rectangular has descriptive content and little or no emotive content. When a viewer describes a painting as being nice or good, that viewer is perhaps expressing approval or recommendation. But it is unclear what in particular, if anything, in the painting, nice or good, describes. Nice or good have emotive content and little or no fixed descriptive content. Emotive content is sometimes called connotation. Many adjectives, properties, nouns, have both some descriptive content and some emotive content. And it is possible for different words to have the same descriptive content but different emotive content. For example, there are Bertrand Russell's well-known emotive conjugations. Comment. Brains Trust, BBC Radio, April 26, 1948, such as, I am firm, you are obstinate, he is a pig-headed fool. I am righteously indignant. You are annoyed. He is making a fuss. Over nothing. 398. We made a tactical withdrawal. Our allies retreated. The enemy was routed. I have reconsidered. You have changed your mind. He has gone back on his word. Were the present offer to be described as firm, or as obstinate, or indeed, as a pig-headed fool, the descriptive or cognitive content of those ascriptions is exactly the same, we may suppose. That is the dispositions and actual actions of his that these concepts or labels pick out, if correctly used, are identical for all three labels. However, the labels are intended to either express or evoke different sentiments on the part of the speaker or the listener. Roughly, at one end, a speaker that uses firm is mildly admiring of the trait and wishes the listener to be mildly admiring also. At the other end, well, we all know what labeling the author, a pig-headed fool, is intended to achieve. These expressive or evocative functions are the emotive content. So, each of the concepts, firm, obstinate, pig-headed, has pretty well the same descriptive content, the same intentions, but they differ in emotive content. They are synonyms in all but emotional force. Of course, both descriptive content and emotive content of particular labels or concepts can change through time and be different across cultures. For various reasons, usually obvious ones, individuals, groups, and institutions often try to employ different labels or different classification schemes in order to manipulate the emotive-descriptive divide in a way they wish. For example, it may be that the label garbage collector is a term of mild opprobrium, and all concerned might switch to sanitary engineer as the concept or label of choice. Here, the intentions of garbage collector 399 and sanitary engineer are pretty well the same, but one has unwanted emotional association. This move is usually a temporary palliative. Say folk do have bad feelings to, or opinions of, the profession of garbage collection. Those bad attitudes do not attach to the name, rather they attach to what those garbage collectors are and to what they do. We are all familiar with Romeo and Juliet's "What's in a name?" That which we call a rose by any other name would smell as sweet. Using the label sanitary engineer might work for a while, but give it 50 years and a person may be able to insult another with the words sanitary engineer. A point 6 classification schemes and the act of classification. There are two balls that we are juggling here. There are the classification schemes, and there is the act of classification. Consider, for example, the aforementioned nursing intervention classification, Butcher et al. 2018. It is a perfectly fine classification, absolutely clear as to what it is and what it is supposed to do. Then there is the act of classification, i.e., deciding what interventions a nurse or healthcare provider have done on a particular occasion. As an example, the entry for activities relating to hypertension includes 50 to 100 activities. Here are a brief few of those. Instruct at-risk patients to have regular preventative health screenings, including electrocardiogram, echocardiogram, electrolytes, urinalysis, as indicated. Instruct related to healthy dietary pattern. Instruct related to proper physical activity, e.g., exercise 30 to 45 minutes a day. Instruct related to contributing lifestyle habits that should be avoided, e.g., use of tobacco in any form and alcohol. 400. Instruct the patient on lifestyle modification related to sleep and rest patterns, e.g., 8 hours per night is recommended. Provide information on possible changes in lifestyle necessary to Avoid future complications and control the disease process. Provide information related to the purpose and benefit of the lifestyle changes. Instruct related to self-blood pressure monitoring and to report abnormal findings. Instruct the patient on possible causes of hypertension. Instruct the patient and family to take an active role in the management of disease process, e.g., medication indications and administration, maintaining proper diet, exercise, and healthy habits, quitting smoking, reducing stress, reducing weight, reducing sodium intake, reducing alcohol consumption, increasing exercise, as indicated. Instruct the patient and family on medication usage and indications. Encourage the patient and family to maintain a list of current medications and reconcile routinely at wellness checks, hospital visits, or hospital admissions. Instruct the patient to recognize and avoid situations that can cause increased BP, e.g., stress or sudden discontinuation of drug treatment. Butcher et al. 2018, pages 213 to 214. Suppose a nurse interacts with a hypertension patient and there is a serious back and forth medical conversation. A question is, which of these activities has the nurse done? No doubt the nurse himself and the local general medical environment know reasonably well. The point being made here is that the act of classification, deciding which items belong in which classes, is fallible, and it is subject to mistakes and possible even to deliberate misuse or malfeasance. 401. A point 7 annotated readings for Appendix A. Frick, Martin. Logic and the Organization of Information. New York, Springer, 2012. Frick, 2012. This has material on organizational structures and graph theory, and further references that are relevant. 402. Appendix B, Working with LLMs. B.1 Introduction. Do yourself a favor. Learn as much as you can about LLMs. You can go a long way merely by getting access and by typing. You can go further by having the computer programming language Python on your computer and using an LLM development environment like LangChain. Many of the major LLM implementations are readily available. As examples, Bard, using Lambda, is available from https://bard.google.com. It is free. Bard implementations will usually have a microphone icon and can take spoken or dictated input. That will make interactions quicker. GPT-4 and ChatGPT are available from https://openai.com. Some modes of access are free. Others can be paid for either by usage or by monthly subscription. Current subscription to GPT Plus is $20 a month. With a subscription, the page https://chat.openai.com. Access to GPT 3.5 and GPT-4, and to plugins and web browsing enhancements. There are about 120 plugins available at the moment, with many more to come, no doubt. You are allowed to have 3 plugins enabled at one time. The author has Wolfram, which gives mathematics and more reliable facts and factual statistics, Scholar AI. 403. Which helps with scientific papers and prompt perfect. Separately, the author has an API, Application Programming Interface, key to GPT APIs. This is for programs using a GPT LLM and is charged by the access, usually just cents for a day's work. More on the programming later. ChatGPT is also available as a free app for the iPhone, and there will B, a free app for Android phones. Bing, a search engine using GPT-4, is available on a web browser as an app for smartphones as part of a chatbot voice assistant on Amazon Echo and Google Home. New Bing is available from https://www.bing.com/new. We are going to use Application Programming Interfaces, API, for interacting with the LLMs. A valuable resource with many links to materials is OpenAI Cookbook, OpenAI 2022-2023. B.2 Prompts and Prompt Engineering. An LLM takes some text or images or sounds as an input prompt and returns text or images or sounds as its response. For our purposes, we will generally assume that prompts are given as text in English. Crafting a prompt to obtain the right or desired kind of response is prompt engineering. Prompt engineering is an active research area with hundreds of publications. There are also many excellent educational sources for learning prompt engineering. One example is the Prompt Engineering 404 Guide, Saravia 2023, created by Elvis Saravia of Dare.ai, democratizing artificial intelligence research, education, and technologies. That work is clear and comprehensive. We will sketch or paraphrase some of it to give you, the reader, some idea of the strengths and weaknesses of prompt engineering. A point to be made is that you never really know what you are going to get as the output from an LLM using a prompt. For a start, the relationship between the prompt and the response is probabilistic and usually exactly the same prompt can produce 2 or 3 different responses. If the LLM produces these automatically, they are sometimes called drafts. Then there is the fact that the textual prompts are given in natural language, say English, and any natural language has a penumbra of uncertainty and ambiguity about meaning. In computer programming, the programs are usually written in a programming language, say Haskell, which has a formal definitive syntax and semantics. There is no doubt whether an expression in the language is well-formed and no doubt as to what it means. In contrast, the LLMs are being prompted by textual strings, which may or may not be correct English and which may or may not have an unambiguous meaning. Then the response, the output, is also in possibly ambiguous English in an intended or unintended format. These considerations suggest that there is a trial and error, an experimental aspect to prompting and prompt engineering. In some contexts, this might not matter when writing fiction, for example. But in other contexts, for example, when generating coherent and logically sound legal arguments, it might be important. 405. B.2.1 Basic examples of zero-shot prompting. Zero-shot prompting is where you just give the instructions in text. You do not give examples or shots. No demonstrations are allowed and only an instruction in natural language is given to the model. Brown et al. 2020, 5. Here are some examples of the following typical NLP processes of interest to us. Explanation, text summarization, information extraction, question answering, text classification, conversation, code generation, reasoning, explanation. The prompt. Explain prompting used in large language models. GPT 3.5 replies. Prompting is a technique used in large language models like GPT-3 to generate desired responses or outputs. When using a language model, you typically provide it with a prompt, which is a Short piece of text that frames the context or question for the model. The model then generates a continuation of the prompt, based on its training and the patterns it has learned from the data. Prompting serves multiple purposes. Context setting. The prompt helps establish the context for the model, giving it is capable of generating coherent and contextually relevant responses based on provided prompts. What is a good way to learn how to use a LLM? Please keep your answer brief. Bard, with the option to view other drafts. Here are some good ways to learn how to use a LLM. Read the documentation. Most LLMs come with extensive documentation that explains how to use them. This is a great place to start learning the basics of how to interact with the model. Take a tutorial. There are many tutorials available online that can teach you how to use a LLM. These tutorials can be a great way to learn the basics of how to use the model and how to apply it to different tasks. Experiment. The best way to learn how to use a LLM is to experiment with it. Try different prompts and see what kind of responses you get. You can also try using the model to complete different tasks. Join a community. There are many online communities where people discuss LLMs. These communities can be a great resource for learning new things about LLMs and getting help from other users. Here are some additional tips for learning how to use a LLM. Start with a simple task. When you're first starting out, it's best to start with a simple task. This will help you learn the basics of how to interact with the model without getting overwhelmed. Be patient. LLMs can be slow, especially when they're first being trained. Be patient and give the model time to generate a response. 408. Don't be afraid to ask for help. If you're stuck, don't be afraid to ask for help from other users or from the documentation. With a little practice, you'll be using LLMs like a pro in no time. Text classification. Is the following text friendly or confrontational? Text, hey you get off of my cloud. Bard. The text, hey you get off of my cloud, is confrontational. It uses the words hey and get offa, which are both informal and aggressive. The sentence also contains a direct command, which can be seen as rude. Here are some ways to make the text more friendly. Excuse me, but could you please get off my cloud? I'm sorry, but I need to use my cloud. Could you please move? Would you mind getting off my cloud? I need to use it. These sentences are all more polite and less confrontational than the original text. They also use more formal language, which can make the request seem more reasonable. Conversation. Hello, how are you? GPT for no plugins. Hello. As an artificial intelligence, I don't have feelings, but I'm here and ready to help you. How can I assist you today? Would you like to hear how I am? ChatGPT 4. Of course. I'm here to listen. Please feel free to share how you're doing. Code generation. 2 examples. Write code to add up some numbers and return their average. ChatGPT 4. 409. Sure, here's a simple Python function to calculate the average of a list of numbers. Def average, numbers. Return sum, numbers, /len, numbers. Numbers equals 1, 2, 3, 4, 5. Print, average, numbers. In this code, the average function takes a list of numbers as an argument. It uses the built-in sum function to add up the numbers, and the len function to find how many numbers there are. It returns the sum divided by the count, which is the average. The list numbers is defined as an example, and the average of its values is printed. Please replace the numbers in the list with the numbers you'd like to calculate the average for. Write a parser to parse Lisp expressions. GPT-4. Sure, here's a very basic recursive list parser written in Python. This parser will be able to handle simple Lisp expressions like add 1, 2, or mul, add 1, 2, add 3, 4. Please note that this is a basic implementation and does not cover all aspects of Lisp. It's a simplified version to give you a head start. Deth parse underscore Lisp, expression. Deth tokenize, expression. Return expression dot replace, comma. Dot replace, dot split. Deth read underscore from underscore tokens, tokens. If len, tokens, equals 0. Raise syntax error, unexpected EOF. Token equals tokens dot pop, 0. If token equals L equals. While tokens, 0, equals. L dot append, read underscore from underscore tokens, tokens. 410. Tokens dot pop, 0, hashtag pop off. Return L. L if token equals. Raise syntax error, unexpected. Else. Try, return int, token. Accept value error. Try, return float, token. Accept value error, return. str, token. Tokens equals tokenize, expression. Return read underscore from underscore tokens, tokens. Hashtag example usage. Print, parse underscore Lisp, add 1, mul 2, 3. This code takes a Lisp expression as input, tokenizes it, splits it into separate parts, and then recursively parses the tokens into nested lists. Symbols are kept as strings, and numbers are converted to integers or floats. Remember that this parser won't actually evaluate the list expressions, it just parses them. If you want to evaluate them as well, you'll need to implement an evaluator that understands the different Lisp functions, like add, mul, etc. / note from MF. This is not an off-the-chart difficult challenge, but it is not trivial either. The answer is pretty impressive. */ Reasoning. The detective reasoned. If there is blood on the knife, the butler committed the crime. There is no blood on the knife. Therefore, the butler did not commit the crime. Is this valid reasoning? GPT-4. The reasoning here seems to follow the format of modus tollens, which is a valid form of argument in classical logic. However, the 411 initial conditional, if there is blood on the knife, the butler committed the crime, may not be necessarily true in all cases. Modus tollens reasoning goes like this. 1. If P, then Q. 2. Not Q. 3. Therefore, not P. In this case, 1. If there is blood on the knife, P, then the butler committed the crime, Q. 2. There is no blood on the knife, not P. 3. Therefore, the butler did not commit the crime, not Q. While it is valid reasoning according to modus tollens, it is contingent on the truth of the initial conditional statement. In this case, the conditional statement seems to suggest that only the butler could have left blood on the knife, which is quite an assumption. The blood could have come from someone else, or the butler might have cleaned the knife, for instance. Therefore, while the logic is structurally sound, the premises, the assumptions or facts that the argument is based on may not be valid, and thus the conclusion could potentially be flawed. / note from MF. GPT-4's answer here basically is completely wrong. It pulls up modus tollens, which is fine. But then it muddles up its PS and QS. Look at the lines numbered 2. The modus tollens schema requires not Q, but then it uses not P as an instance of that. GPT-4 is attempting reasoning, but does not succeed in this case. */ B.2.2 Examples of few-shot prompting. Few-shot prompting covers cases where examples are given. Outside of LLMs, it is very common when giving instructions to give at least one example of what is required, say, when teaching mathematics or passive voice construction in English writing. Most LLMs can work just from examples. They do not need the instruction or explanation. 412. Here is an example of one-shot. The LLM has been given a single example of an English to French translation and, without even being told what the task is, it has figured out what to do and has done it. See otter equals loutre de mer. Peppermint equals GPT-4. The translation for peppermint in French is Mont Poivre. While this is an example of one-shot prompting, it is unclear how good it is. As a test of the LLM, it is from Brown et al. 2027. That is the main research paper on few-shot prompting. The LLM may have seen it thousands of times during training. Here is an example of many-shot. Cat equals cats. Rabbit equals rabbits. Mouse equals GPT-4. The plural form of mouse is mice. You can see here how problems might arise. The LLM needs to spot the pattern. The two examples can be construed either as forming the plural form or as adding the letter des on the end of a word or noun. Cat equals cats. Rabbit equals rabbits. Mouse equals mouses. Man equals mans. Woman equals 413. GPT-4. The plural of woman is woman. Then CTT equals CTTS. Bit equals bits. Zouse equals zouses. MNN equals MNNS. Woman equals GPT-4. Following the same pattern you've established with the other words, the transformation of woman would be womans. However, it's important to note that in standard English, the plural of woman is woman. It is just too clever. B.2.3 Chain of Thought Prompting. Jeff Dean writes, one of the broad key challenges in artificial intelligence is to build systems that can perform multi-step reasoning, learning to break down complex problems into smaller tasks and combining solutions to those to address the larger problem. Dean 2023. When ChatGPT came out, say November 2022, it was clear the available LLMs were weak in this area. Plainly, they could not do mathematical, logical, and scientific reasoning. It was found that to a degree this could be ameliorated by asking the LLM to show its reasoning, to show the steps it made, i.e. to show its chain of thought. Wei and Zhou 2022, Wei et al. 2023, one of the examples that Jason Wei and Denny Zhou give is this. 414. Figure 28. Standard prompting and chain of thought. Prompting, Wei and Zhou 2022. There is a one-shot prompt here, showing an example, and the example displays the reasoning. It soon became clear that this could be done zero-shot, without examples, merely by adding to the original prompt. Let's think step by step. Then this adjustment of the prompt could be done automatically, for example, by the use of templates, which we will get to. This is an ongoing area of experimentation and discovery. Getting the LLM to think step by step and to show its reasoning is a good idea. 415. B.2.4 Tuning or configuring the models or prompts. Most LLMs have a parameter, temperature, that can be set prior to prompting. The background explanation of this is that an LLM's response involves a choice among probabilities. For example, with closed task like London is the capital city of mask. There will be several possibilities for the blank, e.g. England, culture, fashion, progress, etc., and these will have different probabilities. Now, if the LLM always shows as the most probable response to a word, phrase, sentence, etc., it will always give the same answer. You might not want this. For example, if, on different romantic occasions, like date night once a week, you asked for a love poem for your sweetheart, you presumably would not want the same poem each time. On the other hand, if the LLM always shows his improbable answers, the answers may be interesting and humorous, but also often plain wrong. So, there is a parameter, temperature, which adjusts for this. A higher temperature means that the LLM is more likely to generate creative and interesting answers, while a lower temperature means that LLM is more likely to generate factual and accurate answers. Temperature is in the range 0 to 1 and it would ordinarily be set by default to 0.7. In the case of Bard, it can be set using the following syntax. Bard.generate, prompt, temperature equals 0.5. For example, 416. Bard.generate, London is the capital city of, temperature equals 0. The syntax for setting the temperature in other LLMs may well be different. We know that typically the large models can make mistakes. They are not 100% reliable. GPT-4v is no different in this regard. We also know that the models can give two contradictory answers to the same prompt in the same context. That such answers are contradictory means that one of these answers is false. That is, more generally, the models can give false answers. Also, in more than a few cases there can be no practical means for the user to check the answer. For example, Figure 29. GPT-4v on prime numbers. This answer may be right, or it may be wrong. Typical users would have no idea how to check which it is, or whether they should repose trust in what GPT-4v is telling them. 417. There are ways to improve the quality of answers. There are two standard techniques: imposing constraints and giving the LM or LLM a reputation. Constraint prompting is requiring the LMM to answer in a restricted, constrained way or format. For example, one constrained prompt to read a driving license would be Figure 30. Screenshot of GPT-4v reading a driving license from Yang et al. 2023. This is better than just prompting the LMM to read the text in the image. Notice that it has made a mistake with the hair. As explained in sections 3.10 and 4.7, base models of LMMs are trying only to produce the next word as output. They need further training to become instructor-tuned or fine-tuned LLMs. But even at this point, they are 418. Only doing an extension of their training. Many kinds of instruction or prompting can invoke an activity without necessarily emphasizing that the outcome be correct or true. Yang et al. Mention in their paper the prompt. Count the number of apples in the image, where the image is of apples laid out in rows and columns, Yang et al. 2023. Now, depending on its training, An LMM can count without really focusing on producing a correct answer. A better style of prompt conditions on good performance. An example. Prompt for the Apple image would be, "You are an expert in counting things." In images. Let us count the number of apples in this image by 10. Give detailed instructions on how to do it and how to check the answer. Some of the recent LLMs accept both system prompts and other prompts. A system prompt could then be used to set the system as being in the context where it was an expert in counting objects in images. This use of system prompts is often used to enhance steerability. If you would like to steer an LLM to be an expert in counting or to answer in the style of Emily Dickinson, you would use a system prompt to do it. B.3 Choices on development. Most ML programming work will either use Python or allow Python to be used. In turn, Python is generally available on Macs, Windows, and Linux machines. Python will use pip, which is a package installer. Pip will usually be installed automatically with Python. To check whether you have what is needed, use a terminal and try the following 3 commands. 419. Python 3 version. Python 3.11.3. Where Python 3. /library frameworks python.framework/version/3.11/bin/pyth. On 3. /library frameworks python.framework/version/3.8/bin/pytho. And 3. /usr/local/bin/python 3. /usr/bin/python 3. %pip version. Pip 2 3.1.2 from /library frameworks python.framework/version/3.11/lib/pyth. On 3.11/site packages/pip python 3.11. The response to you on your machine should be somewhat similar, although probably not exactly the same. If you seem not to have Python, go to https://www.python.org and install it. To give you a general idea where we are going here, we are not going to create any LLMs, which would take months and might cost tens of millions of dollars. We are going to work with existing LLMs, e.g. GPT-4, using their APIs. We will send some messages and get replies, both of which we can process as we would like. There will be short Python programs, usually around 50 lines, to do the work. Typically, these Python programs will have import statements at the top, for example, import LangChain. From langchain.llms import OpenAI. 420. From langchain.utilities import Wikipedia API wrapper. #LangChain. This is a convenient host system for working with LLMs. #OpenAI gives us the API to GPT-3, GPT-4, etc. Wikipedia API wrapper allows us to ask for material from Wikipedia. Of course, starting out you will not have the OpenAI and other packages on your computer. This is where the Python package installer pip comes into play. There will be commands like %pip install our requirements.txt, %pip install LangChain, where the requirements file has a list of, surprise, the requirements. You do not need to worry about this right now. As to foundation models, the LLMs, they can be proprietary or open-sourced. Proprietary are closed-source models, usually vastly expensive to make and are owned by commercial companies. That they are closed-source means that the source computer code is not available to you. You cannot see it, you do not know what it is. This does and does not matter. It does not matter in that there is no possibility of you altering the code and re-pre-training the model, because that might cost $10 million, which you do not have to spare. It does matter in that whoever owns the code might change it or withdraw it. They might have a huff, stop playing the game, and take their ball and go home. It also matters in that closed source may be preferable in that it presumably keeps powerful code out of the hands of 421 bad actors. It may be possible to get some kind of closed source version of a foundation model which has locked-in parameters that might protect you from malfeasance or monopolistic behavior by the model's owner. If LLMs develop as it seems they are going to, the models will have a role somewhat similar to public utilities. We need to be cautious when letting private companies have control of public utilities. Some foundation models have been open-sourced and are freely available to all to use, see, or develop. Hugging Face provides a hub, a library of open-source foundation models. Hugging Face 2023. When you work with the APIs of OpenAI or with Hugging Face or with Pinecone, you will need to get an API key. Getting these may vary a little from host to host. In the case of OpenAI, go to their website https://openai.com, create an account, then view API keys under your profile, and proceed from there. There are charges. Typically, they will is associated with lung cancer. Lung cancer is associated with smoking. Variables can be independent of each other. There is also the notion of conditional dependence and independence. The various structures of the graphs, the chains, forks, and collisions give rise to the various dependencies. They give rise to complex statistical predictions that can be tested. For example, the very simple causal diagram. Figure 50. A chain from smoking to lung cancer mediated by cell mutation entails that smoking is correlated with lung cancer and not conditionally correlated with lung cancer when cell mutation is controlled for. If either of these statistical predictions are mistaken, so too is the original causal diagram. 463. There is a technique, in fact an algorithm, deseparation, direction separation, that can convert a causal diagram into all the statistical predictions that it entails. To sum up this whole presentation in a simple way, if there are forks, there needs to be conditionalization on the common causes. If there are collisions, there needs to be no conditionalization on the colliders. The importance of the causal diagrams is this. Almost all, maybe even all, machine learning is about what causes what, about learning about causality. Machine learning, and all other kinds of empirical science for that matter, never has anything more to work with than correlations. They all have to make the leap from correlation to causation. There is no way this can be done infallibly. There is no way it can be done without assumptions. But causal diagrams provide a framework for making assumptions and for suggesting the appropriate correlations to test. Let us conclude by sketching two examples of how causal diagrams might be used in connection with bias. Matt Kussner et al. Introduced the example of predicting the first-year average grade, FYA, of students in law school. Kussner et al. 2018. They write, the Law School Admission Council conducted a survey across 163 law schools in the United States, 35. It contains information on 21,790 law students, such as their entrance exam scores, LSAT, their grade point average, GPA, collected prior to law school, and their first-year average grade, FYA, 464. Given this data, a school may wish to predict if an applicant will have a high FYA. The school would also like to make sure these predictions are not biased by an individual's race and sex. However, the LSAT, GPA, and FYA scores may be biased due to social factors. Kussner et al. 2018. A causal diagram for this might be Figure 51. Law School First-Year Average Grade, Kussner et al. 2018. This asserts that race non-deterministically affects GPA, LSAT, and FYA, as does sex. In this problem, it is imagined that the law schools want to predict first-year average grade FYA, and they cannot use race and sex as these are protected. The next step is to realize or take into account that knowledge, a student's knowledge, also affects GPA, LSAT, and FYA, and this gives a second causal diagram. 465. Figure 52. Law School First-Year Average Grade with Student Knowledge, Kussner et al. 2018. With this causal diagram, some mathematics can be done on the forks, collisions, and the data that can produce the requisite predictions of FYA from LSAT and GPA without using the protected attributes of race and sex. The law schools would be able to prove the predicted FYA is not biased. Typically, the diagrams are more complex. This one from Tyler Vanderweel and Nancy Stott relates legal cases and their case characteristics to both judicial decisions and the likelihood that litigation will take place in courts with judges of a particular race, gender, age, or ideology, for plaintiffs prefer to file claims with judges deemed friendly to their legal claims. Vanderweel and Stott 2011. 466. Figure 53. A depiction of possible factors in a judicial decision. Vanderweel and Stott 2011. In sum, if there is an assertion of bias in allocation, say, perhaps with allocation of mortgages or allocation of places in a law school, suitable causal diagrams might be able to highlight relevant correlations to be investigated. In turn, these might be able to produce evidence, within the bounds of fallibility, that there is no bias. The diagrams provide a structure for investigation false positives and false negatives. Separately, explainable artificial intelligence, XAI, is important. Explanations need causes. Causal diagrams are a stepping stone, along with data and correlations, towards identifying causes. 467. D.3 Annotated readings for Appendix D. Hernan, Miguel. Causal diagrams, draw your assumptions before your conclusions. edX, 2022. https://www.edx.org/course/causal-diagrams-draw-your-assumptions-before-your. Hernan 2022. Mient, Leslie. Key Structures in Causal Graphs, 2020. https://www.youtube.com/watch?v=UA0VYBNZ9U. Mient 2020, Leslie Mient, has posted many excellent videos on statistics and causality. This is a relevant example. Rohrer, Julia M. Thinking Clearly About Correlations and Causation, Graphical Causal Models for Observational Data. Advances in Methods and Practices in Psychological Science 1, Number 1, 2018 27-42. https://doi.org/10.1177/251524597745629. Roar 2018. This is a masterpiece. It is probably a little advanced for us. 468. Appendix E, Knowledge Graphs. E.1 Knowledge Graphs. A knowledge graph is a means of representing knowledge. Its relevance to us is that is a technology or technique that can help with the search and discovery of information. It is not in itself an artificial intelligence or machine learning technique. However, it can be part of an infrastructure that supports some applications of machine learning in librarianship. Conceptually, a knowledge graph starts with a node representing an object, which might be a person, a place, or a thing, or a date, or etc., then adds as links facts about that object. Here is a very simple knowledge graph. Figure 54. A simple knowledge graph, W3C Working Group. 2014. 469. Typical knowledge graphs will be much more complicated than this. Google. Have a knowledge graph technology, Google Knowledge Graph. As of 2012. This had 500 million objects and 3.4 billion facts in it, single 2012. Google populate their knowledge graph using search data that they have from users. For example, if the search, "Who painted the Mona Lisa?" was popular, the answer to that search would be added to the knowledge graph. As a fact, usually, a knowledge graph is a data structure that computer programs can use in the background, as opposed to the user exploring it visually. No user is going to look through a graph of 500 million objects. Some possibilities for knowledge graphs are: 1. Helping disambiguate. For example, were there to be several Bob objects in the graph, the user or system would know that disambiguation was required for queries about Bob and maybe suggest facts to do it. 2. Helping with creating summaries of information about an object. For example, it could help identify key facts, say about the Mona Lisa. 3. Pointing the user to further popular, or rare, queries or information about the objects. 4. Being part of a question-answering system, for example, who painted Mona Lisa? 470. 5. Being part of a recommender system, for example, by extracting the preferences of similar people in the graph. E.2 Annotated readings for Appendix E. Pang, Cun, Fong Xia, Mehdi Nazar Parsa, and Francesco Osborne. Knowledge graphs, opportunities and challenges. Artificial Intelligence Review 56, Number 11. 2023 13071-102, https://doi.org/10.1007/S10462-023-10465-9, Peñadal. 2023. 471. Glossary. There are many excellent ML glossaries available online, for example, Google's Machine Learning Glossary, ML Fundamentals, Google 4. Developers 2023, we are using and editing parts of that here. There are also explanations of key concepts, approaching them from a librarianship point of view, for example, Brady Lund and Ting Wang's chatting about ChatGPT, how may AI and GPT impact academia and libraries? Lund and Wang 2023. Generally, we are restricting ourselves to technical or unusual terms that appear in this text. A. Accuracy. The number of correct classification predictions divided by the total number of predictions. Application Programming Interfaces, APIs. The protocols that allow outside programs to use or communicate with an application. Algorithm. 1. A step-by-step computational procedure. 2. Any piece of computer software, especially software that can make decisions independent of a human decision maker. 472. Alignment. That the model's predictions or behavior correspond closely with the expected or desired or intended outcome. Anaphora. The use of pronouns or other words to refer back to previously mentioned subjects or objects. Artificial intelligence, AI. The use of computers, algorithms, and sometimes outside data to solve problems that an ideally rational and intelligent human being would be able to solve, given the time, resources, and ingenuity. Artificial General Intelligence, AGI. A non-human mechanism that demonstrates a broad range of problem solving, creativity, and adaptability. Artificial Superintelligence, ASI. Is the possibility that AGI becomes established and then the AGI machines simply design themselves and become smarter and smarter in a runaway fashion. 473. Attention. A technique that enables models to dynamically focus on certain parts of the input for better performance, especially in sequence-to-sequence tasks. B. Bag of words. A representation of the words in a phrase or passage, irrespective of order. Bias, ethics/fairness. 1. Unfairness by means of stereotyping, prejudice or favoritism towards some things, people, or groups over others. 2. Errors in input data or output predictions, independent of questions of fairness or unfairness. C. Cause or causal factor. A. X and Y occur. B. X precedes Y in time. C. The presence of X raises the probability of Y. And D. Had there been an intervention that changed X, that would change the probability of Y. For example, the diagnosis that smoking caused lung cancer in a group of patients amount to A. The patients smoked and have lung cancer. B. The patients smoked before they got lung cancer. C. Their smoking raised their probability of getting lung cancer. And D. Had they not smoked in the first place, their probability of getting lung cancer would have been lower. 474. Chain of thought, COT, prompting. Encouraging a large language model, LLM, to explain its reasoning, step by step. For example, consider the following prompt, Kane particular. Attention to the second sentence. How many G-forces would a driver experience in a car that goes from 0 to 60 miles per hour in 7 seconds? In the answer, show all relevant calculations. Chain of thought prompting forces the LLM to perform all the calculations, which might increase the chances of the answer being correct. In addition, chain of thought prompting enables the user to examine the LLM stats to determine whether the answer makes sense. Chatbot. A computer program designed to simulate conversation with human users, especially over the internet. Class. A labeled collection of items. For example, 1. In a model that detects spam, the two classes might be spam and not spam. 2. In a model that identifies dog breeds, some of the classes might be poodle, beagle, pug. 475. Classification model. Predicts a class. For example, the following are all classification models. 1. A model that predicts an input sentence's language, French, Spanish, Italian. 2. A model that predicts tree species, maple, oak, baobab. 3. A model that predicts the positive or negative class for a particular medical condition. Closed task. a method used in language teaching and as a machine learning task. Such tasks are often referred to as a fill-in-the-blanks task, closed test, gap filling task, or text completion task. It involves having a model fill in missing words or tokens in a sentence or paragraph. Clustering. Grouping related examples, particularly during unsupervised learning. Once all the examples are grouped, a human can optionally supply a label or meaning to each cluster. For example, that cluster 1 is dwarf trees and cluster 2 is full-size trees. Conversational implicature. The meaning that is implied by a speaker but not explicitly stated in the conversational context. 476. Conjectural. Speculative, hypothetical, theoretical, presumptive, or fallible. There is a philosophical view, highlighted by Karl Popper, that all knowledge of the world, and some knowledge of mathematics and logic, are conjectural. Confirmation bias. The tendency to search for, interpret, favor, and recall information in a way that confirms one's pre-existing beliefs or hypotheses. Controlled vocabulary. A standardized terminology, curated term set, or fixed lexicon. It is a predefined set of terms that are used to ensure consistency in the tagging and categorization of content. Constraint prompting. A method to direct a model's generation or response by setting specific constraints or conditions, or by providing a template that should be used for the answer. Counterfactual. Let us start with an example. Napoleon lost the Battle of Waterloo, as a matter of fact. But an adventurous historian might consider the question of what would have happened if Napoleon had won the Battle of Waterloo. Supposing that Napoleon won would be counter to the facts, and a historian's analysis would be a counterfactual analysis. 477. Thinking counterfactually, which we do all the time, especially when making decisions, involves considering alternative scenarios and outcomes that did not happen or might not have happened, but which could have happened under different circumstances. If I'd run faster, I would have caught the bus. If I'd studied harder, I would have passed the exam. If inflation had continued, there would have been a fall in unemployment, etc. Some counterfactuals are true, and some are false. For example, if the aforementioned bus were traveling at 50 miles per hour, no amount of faster running on my part would result in my catching it. Counterfactual reasoning and causal reasoning are often intertwined. Were we to say John Smith's lung cancer was caused by smoking, we in part mean if John Smith had not smoked, he would not have got lung cancer, which is counterfactual. Then, were we to say, if Jane Smith, a non-smoker, were to become a smoker, she would raise the probability of her getting lung cancer. That statement is a true counterfactual supported by a causal connection between smoking and lung cancer. Overall, counterfactuals are a valuable tool in many fields for analyzing and understanding the implications of events and decisions by considering alternatives that did not occur. CPUs, GPUs, and CUDA. A CPU is a central processing unit, the main computing component of a standard computer. A GPU is a graphics processing unit, a computing component originally designed to provide accelerated graphics for video games and similar. Typically, a CPU works serially, one task after another, whereas a GPU works in parallel, carrying out many different tasks at the same time. The company NVIDIA realized that GPUs, which they specialized in, were ideal for artificial intelligence. They produced the 478 CUDA platform, which is for high performance, high throughput computing, not necessarily having anything to do with graphics. As of 2024, most LLM research and commercial work will be using the CUDA platform and NVIDIA electronic chips. D. Data set or dataset. Raw data, commonly organized in one of the following formats. 1. A spreadsheet. 2. A file in CSV, comma-separated values, format. Deep learning, DL. Advanced techniques within the field of artificial intelligence focused on mimicking the operation of the human brain. Deep model. Neural networks containing more than one hidden layer. Deep fakes. Media that have been altered or wholly generated by artificial intelligence to present something that did not actually occur. Examples include manipulated videos which might include realistic speeches from politicians. That simply never happened. 479. Delayed rewards. In many settings there are rewards, such as passing the exam, arriving at the destination safely, finding the cheese in the maze. Delayed rewards are where the agent has to do some exploring of the task or making more than a few steps presumably towards the goal before a reward is given. The above examples have delayed rewards, pressing a button to get a pellet of food. Does not. Digitization. The conversion of text, pictures, or sound into a digital form that can be processed by a computer. Discriminative model. Predicts the appropriate or correct labels for new examples presented to it. For example, a discriminative model might predict whether incoming email was spam. It discriminates between spam and not spam. In contrast, generative models might produce or create completely new examples such as new images or paintings. Most supervised learning models are discriminative models. Dynamic. The terms dynamic and online are synonyms in machine learning. The following are common uses of dynamic and online in machine learning. 480. 1. A dynamic model, or online model, is a model that is retrained frequently or continuously. A dynamic model is a lifelong learner that constantly adapts to evolving data. 2. Dynamic training, or online training, is the process of training frequently or continuously. 3. Dynamic inference, or online inference, is the process of generating predictions on demand. E. Embeddings. Numerical representations of text, concepts, or other types of data as lists of numbers, i.e. they are points or vectors in a high-dimensional space. Empirical. Knowledge or models that are based on observation or experience rather than on pure mathematics or pure logic. Empirical knowledge is tested by means of experiments or observations. Epoch. A full training pass over the entire training set such that each example has been processed once. Example. The values of one row of features and possibly a label. Examples. In supervised learning fall into two general categories. 481. 1. A labeled example consists of one or more features and a label. Labeled examples are used during training. 2. An unlabeled example consists of one or more features but no label. Unlabeled examples are used during inference and use. For instance, a model is being trained to determine the influence of weather conditions on student test scores. Here are 3 labeled examples. Features label. Temperature, humidity, pressure test score. 1547 998 good. 1934 1020 excellent. 1892 1012 poor. Figure 90. Labeled examples. Here are 3 unlabeled examples. Features. Temperature, humidity, pressure. 1262 1014. 2147-1017, 1941-1021. Figure 91. Unlabeled examples. In supervised machine learning, models train on labeled examples and make predictions on unlabeled examples. 482. In semi-supervised and unsupervised learning, unlabeled examples are used during training. Expert system. A computer system that emulates the decision-making ability of a human. Expert. F. Fakes. In machine learning, fakes are the products of algorithms designed to generate deceptive content that mimics the real one. Fallible. Not absolutely certain. Many views, theories, and observation reports are true. Nevertheless, often it is not known with absolute certainty whether they are true. Our knowledge of them is fallible. False negative. An example in which the model mistakenly predicts a member of the negative class. For example, the model predicts that a particular email message is not spam, the negative class, but that email message actually is spam. 483. False positive. An example in which the model mistakenly predicts a member of the positive class. For example, the model predicts that a particular email message is spam, the positive class, but that email message is actually not spam. Feature. An input variable to a machine learning model. An example consists of one or more features. For instance, suppose a model is being trained to determine the influence of weather conditions on student test scores. The following table shows 3 examples, each of which contains 3 features and 1 label. Features label. Temperature, humidity, pressure test score. 1547 998 good. 1934 1020 excellent. 1892 1012 poor. Figure 92. Features with labels. Few-shot learner. A machine learning approach where the, perhaps pre-trained, model is designed to learn information with a small amount of, perhaps additional, training data. 484. Few-shot prompting. Prompting where a few examples are given of what the LLM should do. Fine-tuning. Taking a pre-trained model and adjusting its parameters slightly to adapt to a new but related task. Foundation models. Starting points for creating more specialized machine learning models. Frame. A frame, within machine learning and artificial intelligence, is a data structure for representing a stereotypical situation, like a room and its contents, ordering a meal in a restaurant, or buying an airline ticket. G. Generative. The capability of some models to generate completely new data instances that resemble the training data, for example new images or paintings, or new poems or essays. 485. Genial Understander System. A natural language understanding system which can interact with users' friendly or amiable manner to find out what it is they want and any requisite data to assist in that task, e.g. to discover data for a frame war. Frames. Generalization. Making correct predictions on new, previously unseen data. A model that can generalize is the opposite of a model that is overfitting. GPUs, CPUs, and CUDA. See CPUs, GPUs, and CUDA. Gradient descent. A mathematical technique used in training to minimize loss or error. Gradient descent iteratively adjusts parameters of the model, gradually finding the best combination to minimize loss. Ground truth. Reality. For example, consider a model that predicts whether a student in their first year of university will graduate within 6 years. Ground truth 4. This model is whether that student actually graduated within 6 years. 486. H. Hallucinations. False generations, spurious outputs, or fictitious predictions. It is when a model generates information that is ungrounded or not supported by the input data. Homograph. A word characterized by lexical ambiguity, as it shares the same spelling as another word but has a different meaning, for example, bank of river and bank, financial. I. Inductive bias. Training data, no matter how extensive, is never enough on its own to determine predictions about new unseen data. Assumptions are needed. Those assumptions are inductive bias. Inference. The process of making predictions by applying a trained model to unlabeled. Examples. Interpretability. Explaining or to presenting a model's reasoning in terms understandable to a human. 487. Intersubjective, shared conventional knowledge. Conventional agreements shared by multiple individuals or systems. 4. Example, a library classification system such as the Dewey Decimal System is a shared conventional agreement. K. Keyword search. Retrieving information by matching query terms, keywords, against a set of documents or a database. L. Label. In supervised machine learning, that answer or result portion of an example. Each labeled example consists of one or more features and a label. For instance, in a spam detection dataset, the label would probably be either spam or not spam. In a rainfall dataset, the label might be the amount of rain that fell during a certain period. Labeled example. See example. 488. Language model. A statistical model, a generative model, or a predictive model of language. It is a type of model that can predict the next word in a sentence or help generate text based on previous text. Large language models, LLMs. Usually generative pre-trained transformers. These are highly complex models designed to understand, generate, and translate human language. Layer. A set of neurons in a neural network. 3 common types of layers are as follows. 1. The input layer, which provides values for all the features. 2. One or more hidden layers, which find relationships between the features and the label. 3. The output layer, which provides the prediction. 4. For example, the following illustration shows a neural network with 1 input layer, 2 hidden layers, and 1 output layer. 489. Figure 93. A neural network. M. Machine learning, ML. A program or system that trains a model from input data. The trained model can make useful predictions from new, never-before-seen data, drawn from the same distribution as the one used to train the model. Markov process or chain. A mathematical system that undergoes transitions from one state to another with probabilistic rules that depend only on the current state and not on the sequence of events that preceded it. It is a memoryless model. It knows the state that it is in, but knows nothing of the states before that. The child's game Snakes and Ladders is an example of a Markov process. 490. Modality. A high-level data category. For example, numbers, text, images, video, and audio are 5 different modalities. Model. Any mathematical construct that processes input data and returns output. Phrased differently, a model is the set of parameters and structure needed for a system to make predictions. In supervised machine learning, a model is trained on labeled examples, then, in use, it takes an unlabeled example as input and infers a prediction of the correct label as output. Unsupervised machine learning also generates models, typically a function, that can map an input example to the most appropriate cluster for it. N. Negative class. In binary classification, one class is termed positive and the other is termed negative. The positive class is the thing or event that the model is testing for, and the negative class is the other possibility. For example, 1. The negative class in a medical test might be not tumor. 2. The negative class in an email classifier might be not spam. Neural network. A model containing at least one hidden layer. A deep neural network is a type of neural network containing more than one hidden layer. 491. Example, the following diagram shows a deep neural network containing two hidden layers. Figure 94. A neural network showing hidden layers. Each neuron in a neural network connects to all of the nodes in the next layer. For example, in the preceding diagram, notice that each of the three neurons in the first hidden layer separately connect to both of the two neurons in the second hidden layer. Neural networks implemented on computers are sometimes called artificial neural networks to differentiate them from neural networks found in brains and other biological nervous systems. Some neural networks can mimic extremely complex relationships between different features and the label. 492. Neuron. In machine learning, a neuron is a distinct unit within a hidden layer of a neural network. Each neuron performed does a calculation on its own inputs and decides whether it is activated, i.e., whether it fires or is triggered. A neuron in the first hidden layer accepts inputs from the feature values in the input layer. A neuron in any hidden layer beyond the first accepts inputs from the neurons in a preceding hidden layer. For example, a neuron in the second hidden layer accepts inputs from the neurons in the first hidden layer. The following illustration highlights two neurons and their inputs. Figure 96. A neural network showing some neurons. A neuron in a neural network mimics the behavior of neurons in brains and other parts of nervous systems. 493. Node, neural network. A neuron in a hidden layer. O. Objective knowledge. Factual knowledge and a knowledge of science and mathematics. Offline. Synonym for static. One-shot prompting. Prompting where a single example is given. Online. Synonym for dynamic. Ontology. A conceptual framework, a knowledge representation schema, a semantic framework, or a taxonomy, particularly if it is structured hierarchically. Online inference. Generating predictions on demand. For example, suppose an app passes input to a model and issues a request for a prediction. A system using 494. Online inference responds to the request by running the model and returning the prediction to the app. Optical character recognition, OCR. A technology for text recognition, character reader technology, document digitization, and image-to-text conversion. It converts different types of documents, such as scanned paper documents, PDF files, or images, captured by a digital camera, into editable and searchable data. Output layer. The final layer of a neural network. The output layer contains the prediction. The following illustration shows a small deep neural network with an input layer, two hidden layers, and an output layer. 495. Figure 96. A neural network showing an output layer. Overfitting. creating a model that matches the training data so closely that the model fails to make correct predictions on new data that is not part of the training. P. Panopticon. A prison where all actions of the prisoners are observable by the controlling entity. Parameter. Internal variables that can be adjusted during training to alter the models. Behavior. Suitable, or the best, values for the parameters are learned during training. Paternalism. To act for the good of another person without that person's consent, as parents do for children, Suber 1999. Positive class. The class that is being testing for. For example, the positive class in a cancer model might be tumor. The positive class in an email classifier might be spam. 496. Post-processing. Adjusting the output of a model after the model has been run. Post-processing can be used to enforce fairness constraints without modifying models themselves. For example, one might apply post-processing to a binary classifier by setting a classification threshold such that equality of opportunity is maintained for some attribute by checking that the true positive rate is the same for all values of that attribute. As an example of this, in a mortgage application program, post-processing might check that those living north of the railway tracks get as many mortgages as those living south of the railway tracks. Precision. Consider a search of a library collection for items that are relevant to that search. Precision is the proportion, or percentage, of the returned items that are relevant. So, if everything returned is relevant, precision is 100%. If half the items returned are relevant, precision is 50%. Precision has a companion property: recall. Recall is the proportion, or percentage, of the relevant items in the collection that are returned. If all the relevant items are returned, recall is 100%. If half the relevant items in the collection are returned, recall is 50%. Machine learning uses similar concepts of precision and recall. Precision is the proportion of true positives among the positives in a classification task. If every positive is a true positive, precision is 100%. If half the positives are true positives and half are false positives, precision is 50%. If there are no false negatives, i.e. all the positives are captured, recall is 100%. If half of 497 the positives get classified as negatives, i.e. half of the positives get misclassified as false negatives, recall is 50%. Prediction. A model's output. For example, 1. The prediction of a binary classification model is either the positive class or the negative class. 2. The prediction of a multi-class classification model is one class. 3. The prediction of some models can be a number. Q. Quasi-empirical. Investigative approaches or knowledge that are similar to those of empirical research. That is, they might use observation and experiment in discovery and testing. For example, in mainstream computer science, determining what typical algorithms will do when run is a matter of mathematical proof. There is no need to run the programs or observe them running. Such knowledge is non-empirical. But, in machine learning, often finding out what the software will do is a matter of trying it, observing its behavior, and even conducting experiments. In such areas, the knowledge is quasi-empirical. R. Rater. 498. A human who provides labels for examples. Annotator is another name for rater. Recall. Consider a search of a library collection for items that are relevant to that Search. Recall is the proportion or percentage of the relevant items in the collection that are returned. If all the relevant items are returned, recall is 100%. If half the relevant items in the collection are returned, recall is 50%. Recall has a companion property, precision. Precision is the proportion, or percentage, of the returned items that are relevant. So, if everything returned is relevant, precision is 100%. If half the items returned are relevant, precision is 50%. Machine learning uses similar concepts of recall and precision. If there are no false negatives, i.e., all the positives are captured in a classification task, recall is 100%. If half of the positives get classified as negatives, i.e., half of the positives get misclassified as false negatives, recall is 50%. Precision is the proportion of true positives among the positives. If every positive is a true positive, precision is 100%. If half the positives are true positives and half are false positives, precision is 50%. Recommender system. A system that predicts and provides suggestions tailored to the user's preferences. 499. Reinforcement learning. A learning paradigm that trains algorithms based on a system of rewards and penalties. Reliability. The degree to which a measurement, prediction, or algorithm yields stable, consistent results over multiple runs or data sets. A bathroom scale that always weighs 5 pounds light is reliable, but it is not accurate, and nor are its results valid. Retrieval augmented generation, RAG, is a technique to keep an LLM up to date with what it knows and to be more accurate in its replies. The idea is to give the LLM access to an external database or databases. Then factual prompt questions to the LLM are augmented with the instruction to check with the databases and find supporting facts, references, and citations. As external knowledge grows, there is no need to retrain the LLM. Rather, all that is required is for the databases to be updated, which they usually would be as a matter of course. Say for news articles. Self-supervised. A machine learning technique that involves algorithms that can learn to label, classify, or predict new instances without explicit human-provided. 500. Labels. Once the labels exist, the technique can use standard supervised learning. Semantic search. Meaning-based search, conceptual search, or context-aware retrieval. It uses search algorithms that understand the searcher's intent and the contextual meaning of terms to fetch more relevant results. Sentiment analysis. Computationally determining and categorizing opinions expressed in a piece of text, especially to determine the writer's attitude towards a particular topic. Specification for a computer program. The program design, software requirements, or system design. It outlines the expected functions, behaviors, and structures of the computer program. Static. Done once rather than continuously. The terms static and offline are synonyms. The following are common uses of static and offline in machine learning. 1. Static model, or offline model, is a model trained once and then used for a while. 2. Static training, or offline training, is the process of training a static model. 501. 3. Static inference, or offline inference, is a process in which a model generates a batch of predictions at a time. Static inference. Synonym for offline inference. Stochastic processes. random, non-deterministic, or probabilistic processes. Stochastic psittacosis. This is a joke. Emily Bender describes large language models as being stochastic parrots. Psittacosis is a disease that parrots can have. Hence, stochastic psittacosis captures the shortcomings of large language models. Supervised machine learning. Training a model from features and their corresponding labels. Supervised. Machine learning is analogous to learning a subject by studying a set of questions and their corresponding answers. After mastering the mapping between questions and answers, a student can then provide answers to new, never-before-seen questions on the same topic. Switch transformer. A type of transformer model designed to handle extremely large-scale datasets and models by activating only a portion of the model at a time. 502. Synonym, pair. A pair of equivalent terms, lexical equivalents, alternative terms, or interchangeable words. These are words or phrases that have the same or nearly the same meanings and can be used to provide variety in text or speech, for example, attorney and lawyer. Theory-laden. Observations, especially those using instruments, can be said to be theory-laden, and this means that they are influenced by underlying theoretical frameworks. For example, measuring the temperature of a medical patient using an ordinary glass thermometer takes for granted background theories about the expansion of mercury and glass. That observations are theory-laden does not mean that any or all of them are false or incorrect. It does, however, mean that they are fallible, i.e., caution is needed. They might be mistaken. Token is used in two different ways. Were we to ask, how many letters are there printed below? TTT. The answer, 1, would be talking of the letter T as a type, whereas the answer, 3, is talking of the tokens of the letter T. The second sense of 503. Token concerns small processing units. For example, LLMs have a context window of text. That text consists of tokens, the chunks of text that the LLM looks at. Typically, tokens are larger than individually characters, but smaller than whole words. So, a context window of 1,000 tokens might amount to a context window of 1,000 words. Training. The process of determining the ideal parameters comprising a model. During training, a system reads in examples and gradually adjusts parameters. Training uses each example anywhere from a few times to billions of times. Training set. The subset of the dataset used to train a model. Traditionally, examples in the dataset are divided into the following 3 distinct subsets. 1. A training set. 2. A validation set. 3. A test set. Ideally, each example in the dataset should belong to only one of the preceding subsets. For example, a single example should not belong to both the training set and the validation set. 504. Transformers. A type of model in machine learning known as self-attention models. Transformer architectures, sequence-to-sequence models, or attention-based models. These are particularly powerful in handling sequences of data, such as natural language, for tasks like translation or summarization. True negative. An example correctly predicted by the model as belonging to the negative class. For example, the model infers that a particular email message is not spam, and that email message really is not spam. True positive. An example correctly predicted by the model as belonging to the positive class. For example, the model infers that a particular email message is spam, and that email message really is spam. U. Underfitting. A model with poor predictive ability caused by the model not having fully captured the complexity of the training data. Many problems can cause underfitting, including 1. Training on the wrong set of features. 2. Training for too few epochs. 3. Providing too few hidden layers in a deep neural network. 505. Unfairness. Synonym for one meaning of bias. Unlabeled example. See example. Unsupervised machine learning. Training a model to find patterns in a dataset, typically an unlabeled dataset. The most common use of unsupervised machine learning is to cluster data into groups of similar examples. For example, an unsupervised machine learning algorithm can cluster songs based on various properties of the music. The resulting clusters can become an input to other machine learning algorithms, for example, to a music recommendation service. Clustering can help when useful labels are scarce or absent. For example, in domains such as anti-abuse and fraud, clusters can help humans better understand the data. The validation. The initial evaluation of a model's quality. Validation checks the quality of a model's predictions against the validation set. Because the validation set differs from the training set, validation helps guard against overfitting. Evaluating the model against the validation set can be thought of as the 506. First round of testing and evaluating the model against the test set as the second round of testing. Validation set. The subset of the dataset that performs initial evaluation against a trained model. Typically, you evaluate the trained model against the validation set several times before evaluating the model against the test set. Traditionally, you divide the examples in the dataset into the following 3 distinct subsets. 1. A training set. 2. A validation set. 3. A test set. Ideally, each example in the dataset should belong to only one of the preceding subsets. For example, a single example should not belong to both the training set and the validation set. Validity. Accuracy, correctness, or soundness. It concerns the extent to which a model or method accurately measures or predicts what it is intended to. 507. Bibliography. A 12 Allen Institute for AI. 2022, about ARC, AI2 Reasoning. 2022. https://leaderboard.alenai.org/arc/submissions/about. Abebe, Re-Diet, Moritz Hart, Angela Jean, John Miller, Ludwig Schmidt, and Rebecca Wexler. 2022, Adversarial Scrutiny of Evidentiary Statistical Software. In 2022, ACM Conference on Fairness, Accountability, and Transparency, 1733-46. FACCT 22. New York, New York, USA, Association for Computing Machinery. https://doi.org/10.1145/3531146.3533228. Abaid, Abubakar, Maheen Faruqi, and James So. 2021, Persistent Anti-Muslim Bias. In Large Language Models, YAR14. https://doi.org/10.48550/arcs4.2101.05783. Asemoglu, Darren. 2024, Get Ready for the Great AI Disappointment. Wired, 2024. https://www.wired.com/story/get-ready-for-the-great-AI-disappointment/. Adler, Melissa. 2017, Cruising the Library. Fordham University Press. https://doi.org/10.2307/j.ctt1xhr79m. Ager, Simon. 2023, Omniglot, the Online Encyclopedia of Writing Systems and Languages. 2023, https://omniglot.com. AI Advantage, Igor. 2024, The AI Advantage. YouTube. 2024. https://www.youtube.com/channel/UCHXSLBVVNBVSQ57N1NTQ. AI Community. 2024, Community, AI Advantage. 2024. https://myiadvantage.com/community. https://myiadvantage.com/community. Actor, Saida Nahida, Zichuan Yu, Ashik Muhammad, Tianue O, Alex Bowley, Angel. Alexander Cabrera, Krish Delakia, Chinyen Xiong, and Graham Newbig. 2023. An in-depth look at Gemini's language abilities, AR14. http://arcs4.org/abs/2312.11444. A. Kurek, Ekin, Dale Shermans, Jacob Andreas, Tinyuma, and Denny Zhou. 2022. What learning algorithm is in context learning? Investigations with linear models, AR14. http://arcs4.org/abs/2211.15661. Al-Badi, Walid, Lori Elvandian, Anna O., Magdalena Gamolka, Esther Bravo Govea. Louise N. Charles, Fatima Ari Saugay, et al. 2023. IFLA Trend Report. 2022 Update https://repository.ifla.org/handle/123456789/2456. Alam-Mar, J. 2019, The Illustrated Word 2 Vec. 2019. http://jalammer.github.io/illustrated-word2vec/ Algorithmic Justice League. 2022, Algorithmic Justice League, Unmasking AI Harms and Biases. 2022, https://www.ajl.org. Alfred Abrams, Hannah. 2016, Machine Reading the Primeros Libros, 10, 4. http://www.digitalhumanities.org/dhq/fall/100268/0002668.html. Altman, Sam, Dar 2023. OpenAI Dev Day, Opening Keynote. https://www.youtube.com/watch?v=e9mjukuzk. Amatriane, Xavier. 2023, Transformer Models, An Introduction and Catalog. AR14.org 2023, https://arcs4.org/apps/2302.07730v2. American Association of Law Libraries. 2019, AALL Ethical Principles. AALL. 2019. https://www.allnet.org/advocacy/government-relations/recommended guidelines/ALL-ethical-principles/ 508. American Library Association. 2006, Privacy, an Interpretation of the Library Bill of Rights. https://www.ala.org/advocacy/infreedom/library bill/interpretations/privacy. 2007, Types of Libraries. Text. Education and Careers. 2007. https://www.ala.org/education-careers/library careers site/types-of-library. S. 2008, Office for Intellectual Freedom. Text. About ALA. 2008. https://www.ala.org/aboutala/offices/oef. 2018, Facial Recognition. Text. Tools, Publications and Resources. 2018. https://www.ala.org/tools/future/trends/facial recognition. 2021, Professional Ethics and Code of Ethics. Text. Tools, Publications and Resources. 2021, https://www.ala.org/tools/ethics. Amadei, Dario, Danny Hernandez, Girish Sastry, Jack Clark, Greg Brockman, and Ilya Sutskever. 2019, AI and Compute. OpenAI. 2019, https://openai.com/blog/ind-compute/. ANC 2023. The Open American National Corpus. 2023, https://anc.org. Engwin, Julia, and Jeff Larson. 2016, Machine Bias. Text/HTML. ProPublica. May 23, 2016, https://www.propublica.org/article/machine-bias-risk-assessments-in criminal-sentencing. ANSI/NISO, National Information Standards Organization. 2010, Guidelines for the Construction, Format, and Management of Monolingual Controlled Vocabularies. National Information Standards Organization. https://groups.niso.org/@/group_public/download.php/12591/C39-19. 2005 or 2010.pdf. Anthropic. 2024, Meet Claude. 2024, https://www.anthropic.com/Claude. Araujo, Paula Carina da, Renata Cristina Gutierrez Castagna, and Berger Jorland. 2021. Citation Indexing and Indexes. Knowledge Organization. Also available in ISKO Encyclopedia of Knowledge Organization, eds Berger Jorland and Claudio. Noli, https://www.isko.org/cyclo/citation, 48, 172-101. ARC Prize. 2024, ARC Prize, Official Guide. ARC Prize. 2024. https://arcprize.org/guide. Arlich, Kenning, and Bruce Newell. 2017, Thriving in the Age of Accelerations, a brief look at the societal effects of artificial intelligence and the opportunities for libraries. Journal of Library Administration 57, 789-98. https://doi.org/10.1080/01930826.2017.1362912. Aschenbrenner, Leopold. 2024, Situational Awareness, The Decade Ahead. 2024. https://situational-awareness.ai. Asami, Acefei, Andrea Ko, and Mohsen Nokarizi. 2020, Intelligent Libraries, A. Review on Expert Systems, Artificial Intelligence, and Robot. Library High Tech. 39, 412-34. https://doi.org/10.1108/LHT-02-2020-0038. Eyre, Laurie, and Jim Craner. 2018, Algorithms, Avoiding the Implementation of Institutional Biases. Public Library Quarterly 37, 341-47. https://doi.org/10.1080/01616846.2018.15128111. Bodanau, Dmitry, Kyung-Hyun Cho, and Yoshua Benjo. 2016, Neural Machine. Translation by Jointly Learning to Align and Translate AR14. https://doi.org/10.48550/arcs4.1409.0473. 509. Bhavna, Ankur, Isaac Caswell, Julia Kreutzer, Orhan Firat, Donban Esh, Adifir. Siddhant, Mengmei Nyo, et al. 2022. Building Machine Translation Systems. For the next 1,000 languages, AR14. https://doi.org/10.48550/arcs4.2205.03983. Bereit, Mario. 2018, Literary Warrant, IEKO. 2018. https://www.isko.org/cyclo/literary_warrant. Barokas, Solon, Kate Crawford, Baron Shapiro, and Hannah Wallach. 2017, The Problem. With Bias, From Allocative to Representational Harms in Machine Learning. Special Interest Group for Computing, Information and Society, SIXIS, 2017. Beer, David. 2017, The Social Power of Algorithms. Information, Communication and Society 20, 1-13, https://doi.org/10.080/1369118x.2016.1216147. Bender, Emily M., Timnit Gebru, Angelina McMillan Major, and Schmargaret Schmitchell. 2021, On the Dangers of Stochastic Parrots, Can Language Models Be Too Big? In Proceedings of the 2021 ACM Conference on Fairness, Accountability, and Transparency, 610-23. FACCT 21. New York, New York, USA. Association for Computing Machinery. https://doi.org/10.145/34421888.3445922. Benjamin, Garfield. 2022, #Fuck the Algorithm, Algorithmic Imaginaries and Political Resistance. In 2022 ACM Conference on Fairness, Accountability, and Transparency, 46-57. FACCT 22. New York, New York, USA, Association for Computing Machinery. https://doi.org/10.145/3533146.3533072. Berman, Aaron. 2018, Big Brother is Watching You, The Ethical Role of Libraries and Big data. Choose privacy every day, blog. 2018. https://choose-privacy-everyday.org/the-ethical-role-of-libraries-and-big-data/ Berman, Matthew. 2024, Intro to RAG for AI, Retrieval Augmented Generation. 2024, https://www.youtube.com/watch?v=y08nn230_my. Berman, Sanford. 1971, Prejudices and Antipathies, a tract on the LC subject heads. Concerning People. Jefferson, North Carolina, McFarland and Company Incorporated. 2000, Review of Boker, Jeffrey C., and Starr, Susan Lee. Sorting, Sick. Things Out, Classification and Its Consequences. Progressive Librarian 17. Barry, John N., 1998. Choosing Sides, the Impasse Between Prudes and Purists Has Forced the Issue. Library Journal 123, 46-7. Badia, Adish. 2023, How Can an AI Learn to Write? Choose a famous author, and we'll show you. The New York Times, 2023, section. The Upshot. https://www.newyorktimes.com/interactive/2023/04/26/upshot/gpt-from-scratch.html. Biosphere. 2022, Home Biosphere 2. 2022, https://biosphere2.org. Blay, David M., Andrew Y. Ng, and Michael I. Jordan. 2003, Latent Dirichlet. Allocation. Journal of Machine Learning Research 3:993 1022. Blodgett, Sue Lin, Solon Barokas, Hal Dawn 3, and Hannah Wallach. 2020, Language. Technology is Power, a critical survey of bias in NLP. In Proceedings of the 58th Annual Meeting of the Association for Computational Linguistics, 5454. 76, Online, Association for Computational Linguistics. https://doi.org/10.18653/v1/2020.acl-main.485. Bobrow, Daniel G., Ronald M. Kaplan, Martin K., Donald A. Norman, Henry Thompson, and Terry Winograd. 1977, Gus, A Frame-Driven DIA-OG System, 19. 510. Balakbasi, Tolga, Kai-Wei Chang, James Y. Zhou, Venkatesh Saligrama, and Adam T. Kale. 2016, Man is to Computer Programmer as Woman is to Homemaker. De Biasine Word Embeddings. In 9. Barcelona, Spain. Bomasani, Rishi, Drew A. Hudson, Ehsan Adali, Russ Altman, Simran Arora, Sydney. Voanarks, Michael S. Bernstein, et al. 2022. On the Opportunities and Risks of Foundation Models, AR14. https://doi.org/10.48550/arcs4.2108.07258. Bomasani, Rishi, Kevin Kleiman, Shane Longpre, Sayash Kapoor, Nestor Maslage. Betty Shiom, Daniel Jean, and Percy Leon. 2023, The Foundation Model. Transparency Index, AR14. https://doi.org/10.48550/arcs4.2310.12941. Borg, Chris. 2017, What Happens to Libraries and Librarians When Machines Can Read All the Books. Pharaoh Librarian, blog. 2017. https://chris.board.wordpress.com/2017/03/1/6/what-happens-to-dash-libraries-m-librarians-when-machines-can-read-all-the-dash Boker, Jeffrey C., and Susan Lee Starr. 2000, Sorting Things Out, Classification and Its Consequences. Cambridge, Massachusetts, The MIT Press. Briggs, James, and Franciso Ingham. 2022, Langchain AI Handbook. Pinecone. 2022. https://www.pinecone.io/learn/langchain/. British Library. 2020, Digitized Manuscripts Harley MS 7368. 2020. https://www.bl.uk/manuscripts/fulldisplay.aspx?ref=sign Harley_MS_7368. Brooks, Frederick P., 1975. The Mythical Man Month. First edition Addison Wesley. Brown, Tom B., Benjamin Mann, Nick Ryder, Melanie Subia, Jared Kaplan, Profula. Dhariwal, Arvind Neelkantan, et al. 2020. Language models are few-shot. Learners, AR14. https://doi.org/10.48550/arcs4.2005.14165. Bronan Ernst, Anne, edition 2012. Beyond Foucault, New Perspectives on Benthams. Panopticon. https://www.routledge.com/beyond-foucault-new-perspectives-on-benthams-panopticon/bruno-and-ernst/p/books/9780754668435. Buds, Diana Buds, and Diana Buds. 2017, Biased AI is a Threat to Civil Liberties. The ACLU has a plan to fix it. Fast Company. July 25, 2017. https://www.fastcompany.com/90134278/bias-ai-is-a-threat-to-civil-liberty the-ACLU-has-a-plan-to-fix-it. Bulamwini, Joy. 2016, The Coded Gaze. AJL, Algorithmic Justice League. November 6, 2016, https://medium.com/mit-media-lab/-algorithmic-justice league-3cc41331c5148. 2019, The Algorithmic Justice League. MIT Media Lab, blog. 2019. https://medium.com/mit-media-lab/the-algorithmic-justice-league-3cc41331c5148. 2023, Unmasking AI, My Mission to Protect What is Human in the World of Machines. https://www.penguinrandomhouse.com/books/67035/unmaskingai-by-joy-bulamwini/. Bulamwini, Joy, Vicente Ordonez, Jamie Morgenstern, and Eric Learn Miller. 2020. Facial Recognition Technologies, a Primer. https://assets.website-files.com/5E027CA188C993515404B7/5ed1002058516C11EDC66140_FRTs RMA2020.pdf. Butcher, H.K., G.M. Bielczek, J.M. Doctorman, and C.M. Wagner, eds 2018. Nursing. Intervention Classification. C.AI, 2023. Character.AI, Character.AI. 2023, https://beta.character.ai. 511. Caliscan, Eileen. 2021, Detecting and Mitigating Bias in Natural Language Processing. Brookings, blog. 2021, https://www.brookings.edu/research/detecting-and-mitigating-bias in-natural-language Caliscan, Eileen, Joanna J. Bryson, and Arvind Narayanan. 2017, Semantics Derived. Automatically from language corpora contain human-like biases. Science 356. 6334 183-86, https://doi.org/10.1126/science.al4230. Carlson, Jake, and Lisa Johnston. 2015, Data Information Literacy, Librarians, Data, and the Education of a New Generation of Researchers. http://public.eblib.com/choice/public_record.aspx?p=20390088. Carta, Eileen. 2023, the Pope Francis Puffer photo was real in our hearts. GQ. 2023, https://www.gq.com/story/pope-puffer-jacket-midjourney-ai-meme. Cassels, W. A. Schoenberger, and T. B. Grabois. 1978, Interpretation by Physicians of Clinical Laboratory Results. The New England Journal of Medicine 299, 18. 999-1001, https://doi.org/10.1056/and Cauchy, Louis Augustine. 1847, Méthode générale pour la résolution des systèmes d'équations simultanées. Compte rendu à l'Académie des Sciences 25:536-38. CCP. 2020, Center for Creative Photography. Center for Creative Photography. 2020. https://ccp.arizona.edu/home. Chan, Lois Mai. 2007, Cataloging and Classification, An Introduction. 3rd edition Lanham. Maryland, The Scarecrow Press Incorporated. Chan, Lois Mai, Phyllis A. Richmond, and Elaine Svenonius. 1985, Principles of Book Classification, Eat Wyndham Hume, Editor's Introduction. In Theory of Subject Analysis. Edited by Lois Mai Chan, Phyllis A. Richmond, and Elaine Svenonius. Littleton, Colorado, 48-49. Chase, Harrison. 2022. LangChain. Python. https://github.com/hwchase17/langchain. Chen, Xiongwen, and Dale G. Brockway. 2017, Height Diameter Relationships in Longleaf Pine and 4 Swamp Tree Species. Journal of Plant Studies 6, 294. 101, https://www.srs.fs.usda.gov/pubs/54612. Cherian, Anup, Kwanchuanpeng, Suhas Lohit, Kevin A. Smith, and Joshua B. Tenenbaum. 2023, Are Deep Neural Networks Smarter Than Second Graders? BR14. https://doi.org/10.48550/arcs4.2212.09993. Chang, Wei Lin, Lian Minzheng, Ying Sheng, Anastasios Nicholas Angelopoulos, Tianla. Li, Desheng Li, Hao Zhang, et al. 2024. Chatbot Arena, an open platform for evaluating LLMs by human preference, AR14. https://doi.org/10.48550/arcs4.2403.04132. Cho, Kyung Hyun, Bart van Marienboer, Keller Golser, Dmitry Bodanov, Fethi. Bugers, Holger Schwenk, and Yoshua Benjo. 2014, Learning Phrase. Representations using RNN encoder-decoder for statistical machine. Translation. In proceedings of the 2014 Conference on Empirical Methods in Natural Language Processing, EMNLP, 1724-34. Doha, Qatar, Association for Computational Linguistics. https://doi.org/10.3115/v1/d14-1179. Choice Media Channel, DAR 2022. Artificial Intelligence in Academic Libraries, How New AI Services Can Support Your Library Users. https://www.youtube.com/watch?v=ssg-scale-iq0k. Chalet, Francois. 2019, On the Measure of Intelligence, AR14. https://doi.org/10.48550/arcs4.1911.01547. 512. Chomsky, Noam, and Ramin Murfakray. 2023, ChatGPT and Human Intelligence. Noam Chomsky responds to critics. Mr. Online. 2023. https://mronline.org/2023/04/chatgpt-and-human-intelligence- noam-chomsky-responds-to-critics/ Chomsky, Noam, Ian Roberts, and Jeffrey Wadamo. 2023, Opinion. Noam Chomsky. The False Promise of ChatGPT. The New York Times, 2023, section. Opinion. https://www.newyorktimes.com/2023/03/08/opinion/noam-chomsky-chatgpt-html. Chowdhury, Ruman. 2023, Rumman Chowdhury, Ph.D. Rumman Chowdhury, Ph.D. 2023, http://www.rummanchowdhury.com. Clariant Creative Agency. 2022, Your Guide to Pillar Pages and Topic Clusters. Clariant Creative Agency. 2022, https://www.clariantcreative.com/guide-to-pillar-pages-and-topic-clusters. Clark, Jason A., 2018, 2022. Algorithmic Awareness. Rich Text Format. https://github.com/jasonclark/algorithmic-awareness. Coding Vidya. 2023, Home Coding Vidya, Best Computer Science Portal -. 2023. https://codingvidya.com. Colby, Kenneth Mark, Franklin Dennis Hilf, Sylvia Weber, and Helena C. Kramer. 1972. Turing-like indistinguishability tests for the validation of a computer. Simulation of paranoid processes. Artificial Intelligence 3:199-221. https://doi.org/10.1016/0004-3702-72-90049-5. Collier, Adrian. 2016, The Amazing Power of Word Vectors, the Morning Paper. 2016. https://blog.acolier.org/2016/04/21/the-amazing-power-of-word-vectors/ Common Crawl. 2022, Common Crawl. 2022, https://commoncrawl.org. Cook, John. 2023, Cranky Uncle. Cranky Uncle. 2023, https://crankyuncle.com. Corbett Davies, Sam, and Sherrod Goel. 2018, The Measure and Mismeasure of Fairness, a critical review of fair machine learning, AR14. https://doi.org/10.48550/args4.1808.00023. Cordell, Ryan. 2020, Machine Learning Plus Libraries. LC Labs. Library of Congress. https://labs.loc.gov/static/labs/work/report/cordell-loc-ml-report.pdf. Corrado, Edward M. 2021. Artificial Intelligence, The Possibilities for Metadata. Creation. Technical Services, Quarterly 38, for 395-405. https://doi.org/10.1080/07317131.2021.19737797. Costa, Ricky. 2023, ChatGPT Cheat Sheet. https://neuralmagic.com/ https://www.kdnuggets.com/publications/sheets/chatgpt_cheat_costa.p. DF. Cox, Andrew M., and Sovadeep Mazumdar. 2022, Defining Artificial Intelligence for Librarians. Journal of Librarianship and Information Science. 0961006221142029. https://doi.org/10.11/0961000622114229. Cox, Andrew M., Stephen Pinfield, and Sophie Rutter. 2019, The Intelligent Library. Thought leaders' views on the likely impact of artificial intelligence on academic libraries. Library High Tech 37, 3418-35. https://doi.org/10.1108/LHT-08-2018-0105. Coyle, Karen. 2016, FRBR Before and After. 2016, http://kcoil.net/before-and-after/. Crawford, Kate, Dar 2017. The Trouble with Bias, NIPS 2017 Keynote, Kate Crawford. #NIPS 2017. Neural Information Processing Systems. https://www.youtube.com/watch?v=FMYM_BKWQZK. 513. 2022, Lessons from the Panoptic Sort. International Journal of Communication, number 16, 1632-34. Crichton, Gamal, Simon Baker, Yufan Gua, and Anna Korhonen. 2020, Neural Networks for Open and Closed Literature-Based Discovery. PLOS 115, 5. E02328891. https://doi.org/10.1371/journal.pwn.0232891. Das, Kinnear, Clay J., Cockerell, Anand Patil, Powell Petkovich, Mario Gelini, Stefan Grad, and Mohammed Goldust. 2021, Machine Learning and its Application in Skin Cancer. International Journal of Environmental Research and Public Health 18, 24-13409, https://doi.org/10.3390/IGPH1824134009. Das, Rajesh Kumar, and Muhammad Sharif al-Islam. 2021, Application of Artificial Intelligence and Machine Learning in Libraries, a Systematic Review. AR14, 2112.04573, CS. http://arcs4.org/abs/2112.04573. Data Information Literacy Project. 2023, Data Information Literacy. 2023. https://www.datainfolit.org. Davis, Wayne. 2019, Implicature. In the Stanford Encyclopedia of Philosophy, edited by Edward N. Bazalta, Fall 2019. Metaphysics Research Lab, Stanford University. https://plato.stanford.edu/archives/fall2019/entries/implicature/. Dean, Jeff. 2023, Google Research, 2022 and Beyond, Language, Vision, and Generative Models. 2023, https://ai.googleblogs.com/2023/01/google-research-2022- beyondlanguage.html #generative models. Deepnaker and Florian. 2023, Prompt Perfect, Elevate Your Prompts to Perfection with AI Prompt Engineering. 2023, https://promptperfect.gina.ai. Decker, Harrison, Angel Feria, and Indrani Mundal. 2022, URI Libraries AI Lab. Evolving to meet the needs of students and research communities. Dempsey, Lorcan. 2023a, Generative AI and Large Language Models, Background and Contexts. LorcaandDempsey.net, 2023, https://www.lorcaanddempsey.net/intergen-ai/. 2023b, Generative AI, Scholarly and Cultural Language Models, and the Return of Content. LorcaandDempsey.net, 2023. https://www.lorcaandempsey.net/generative-ai-note-about-content/. Desjardins, Jeff. 2017, How many millions of lines of code does it take? Visual Capitalist. February 8, 2017, https://www.visualcapitalist.com/millions-lines-of-code/. Devlin, Jacob, Mingwei Chang, Kenton Lee, and Christina Tudanova. 2019, BERT. Pre-training of deep bidirectional transformers for language understanding. AR14, 1810.04805, CS, May. http://arcs4.org/ads/1810.04805. Dooland, Thomas A., Jeffrey E., Olgan, Derek Widdinghoff, and Gregory M. Marcus. 2013. Incident atrial fibrillation among Asians, Hispanics, Blacks, and Whites. Circulation 128, 23 2470-77. https://doi.org/10.1131.610/circulationa.113.002449. Dixon, Ben. 2023, How to Customize LLMs like ChatGPT with Your Own Data and Documents, Tech Talks. 2023. https://bdtechtalks.com/2023/05/01/customize-chatgpt-llm-embedding/. Digital 2030. 2022, The Algorithm Literacy Project Understanding Algorithms. 2022. https://algorithmliteracy.org. 514. Dizikes, Peter. 2011, When the Butterfly Effect Took Flight. MIT Technology Review. 2011, https://www.technologyreview.com/2011/02/when-the-butterfly-effect-took-flight/. Dryas, Danny. 2023, Pile ME, an embodied multimodal language model. 2023. https://ai.googleblaw.com/2023/0-e-embodied-multimodal-language.html. Droga, Stefania, Sarah T. Gavu, Ishli Keith, and Tammy Cho. 2019. Inclusive AI. Literacy for Kids Around the World. In Proceedings of FabLearn 2019, 104-11. FL 2019. New York, New York, USA, Association for Computing Machinery. https://doi.org/10.1145/331189.33119004. 2019b Inclusive AI Literacy for Kids Around the World. In Proceedings of FabLearn 2019, 104-11. FL 2019. New York, New York, USA, Association for Computing Machinery. https://doi.org/10.1145/331189.33119004. Duham, Pierre. 1914, La Théorie physique sans objet et sa structure, 2nd ed., comma. Translated by The Aim and Structure of Physical Theory English Translation. Philip Wiener. Paris, Chevalier E.T. Rivière. Economist. 2022, Huge foundation models are turbocharging AI progress. The Economist, 2022. https://www.economist.com/interactive/briefing/2022/06/11/huge foundation models-turbo-charging-AI-progress. Econ Talk. 2023, Adam Mastriani on Peer Review and the Academic Kitchen. EconLib. 2023, https://www.econ-talk.org/adam-mastriani-on-peer-review and-the-academic-kitchen/ Egan, Margaret E., and Jesse H. Shera. 1952, Foundations of a Theory of Bibliography. https://www.jstorg.easyproxy4.library.arizona.edu/stable/4304106#sign-metadata_info_tab_contents. Encyclopedia.com 2019. Encyclopedia.com Free Online Encyclopedia. 2019. https://www.encyclopedia.com. Ex Libris. 2019, Artificial Intelligence in the Library, advantages, challenges, and tradition. https://cdn2.hubspot.net/hubfs/29094474/x%sign 20 libras%sign 20 Intel leak. ins%20 white%20 paper.pdf. Fallis, Don. 2002, Introduction, Social Epistemology and Information Science. Social Epistemology 16, 1-1-4, https://doi.org/10.1080/02691720210132752. 2006, Social Epistemology and Information Science. In Annual Review of Information Science and Technology, edited by Blaise Cronin. Volume 40. Fetus, William, Barrett Zoff, and Noam Shazir. 2022, Switch Transformers, Scaling to Trillion Parameter Models with Simple and Efficient Sparsity, AR14. https://doi.org/10.48550/arcs4.2101.03961. Feigenbaum, EA 1989. Toward the Library of the Future. Long Range Planning 22. 118-23, https://doi.org/10.1016/0024-6301, 89, 90059-9. Fernandez, Peter. 2016, Through the Looking Glass, Envisioning New Library. Technologies: How Artificial Intelligence Will Impact Libraries. Library High Tech? News 33, 5528, https://doi.org/10.1108/LHTN-05-2016-0024. 2023, Through the Looking Glass, Envisioning New Library Technologies AI Text Generators as Explained by ChatGPT. Library High Tech News 40, 311-14. https://doi.org/10.1108/LHTN-02-2023-0017. 515. Fermani, D., Marco Marino, P. Marialdo, and Elena Niedu. 2018, Fords. Knowledge Discovery from the Vatican Secret Archives. In Codice Ratio, Episode 1, Machine Transcription of the Manuscripts. KDD. https://doi.org/10.1145/3219819.3219879. Fermani, Donatella, Paolo Marialdo, and Marco Marino. 2017, In Codice Ratio. Scalable Transcription of Vatican Registers. 2017, https://akimnews.akim.u/and111/special/and-codice-ratio-scalable-transcription-of-Vatican registers. Fitch, Kent. 2023, Searching for Meaning Rather Than Keywords and Returning Answers Rather Than Links. The Code 4 Lib Journal, number 57. https://journal.code4lib.org/articles/17443. FOD, BJ 2003. Persuasive Technology, Using Computers to Change What We Think and Do. San Francisco, California, USA, Morden Kaufman Publishers, Inc. Frick, Martin. 1997, Information Using Likeness Measures. Journal of the American Society for Information Science 48:882-92. 2012, Logic and the Organization of Information. New York, Springer. 2015, Big Data and Its Epistemology. Journal of the Association for Information Science and Technology 66:651-61. 2021, Boolean Logic. Knowledge Organization 48, 177-91. https://doi.org/10.5771/0943-7444-2021-2-177. Frick, Martin, K. Mathieson, and Don Fowlis. 2000, The Ethical Presuppositions. Behind the Library Bill of Rights. The Library Quarterly 70, for 468-91. https://doi.org/10.1086/603218. Friendly, Michael. 2007, Gallery of Data Visualization. 2007. https://www.datavis.ca/gallery/. Froelich, Thomas. 2004, A Brief History of Information Ethics. Bid 13 December. 2004, 2004. Fu, Yao, Haopeng, and Tushar Kott. 2023, How does GPT obtain its ability? Tracing. Emergent abilities of language models to their sources. 2023. https://yaofunatpo-insight/how does GPT obtain its ability tracing emergent abilities of language models to their source CSBA5ACFCFFA1AB-FA1DC. Fuller, Steve. 1988, Social Epistemology, Bloomington, Indiana University Press. Bloomington, Indiana University Press. G2. 2023, Best Bot Platforms Software. G2. 2023. https://www.g2.com/categories/bot-platforms. Gadd, Elizabeth. 2020, AI-based citation evaluation tools, good, bad, or ugly. The Bibliomagician, blog. 2020. https://thebibliomagician.wordpress.com/2020/07/23/AI-based-citation evaluation-tools-good-bad-or-ugly/. Gale, part of Tsinage Group. 2023, Library Marketing, Improve Outreach with Gale. Analytics. 2023, https://www.gale.com/databases/gale-analytics. Gallagher, James, and Piotr Skolsky. 2023, First Impressions with GPT-4v, Ishan. RoboFlow blog. 2023, https://blog.roboflow.com/gpt-4-vision/. Gandhi Jr., Oscar H., 2021. The Panoptic Sort, A Political Economy of Personal Information. Second edition, second edition. Oxford, New York, Oxford. University Press. 516. Gao, Yin Fan, Yun Xiong, Sinu Gao, Kangxian Jia, Jin Lu Pan, Yushi Bai, Yi Dai, Joe Sun, and Haofen Wan. 2023, Retrieval Augmented Generation for Large Language Models, A Survey, AR14. https://doi.org/10.48550/arcs4.2312.10997. Garner, Martin, and Trina Magi, eds 2021. Intellectual Freedom Manual. 10th edition ALA. Editions. https://www.alastereed.ala.org/content/intellectual-freedom-manual 10th edition. GDPR. 2018, Bart. 22 GDPR, automated individual decision-making, including profiling, General Data Protection Regulation, GDPR, blog. 2018. https://gdpr-info.eu/art-22-gdpr/G, Georgia. 2023. Here are the stadiums that are keeping track of your face. Slate, 2023. https://slate.com/technology/2023/madison-square-garden-facial-recognition-stadiums-list.html. Gesser, Avi, Robert Maddox, Anna Gressel, Manisu, Samuel J. Alleman, and Andres S. Gutierrez. 2022. New Automated Decision-Making Laws. 4 Tips for Compliance. Devovoir's Data Blog, 2022. https://www.devovoirs.com/2022/06/25/new-automated-decision-making-laws-4-tips-for-compliance/. Gillies, Mitch. 2020. Amy Johnson, A Brief Biography, Amy Johnson Arts Trust. 2020. http://amyjohnsonartstrust.co.uk/or-life/. GitHub. 2022. GitHub Copilot, your AI pair programmer. GitHub. 2022. https://github.com/features/copilot. Glosek, Elaine. 2021. Your face is, or will be, your boarding pass. The New York Times, 2021, section. Travel. https://www.newyorktimes.com/2021/12/07/travel/biometrics-airports-security.html. Goldman, Alvin I., 1999. Knowledge in a Social World. Oxford, Clarendon Press. Goodman, Bryce, and Seth Flaxman. 2017, European Union Regulations on Algorithmic Decision-Making and a Right to Explanation. AI Magazine 38, 3. 50-57. https://doi.org/10.1609/imag.v38i3.2741. Google Cloud. 2023. Speech-to-Text Supported Languages Cloud Speech-to-Text. Documentation Google Cloud. 2023. https://cloud.google.com/speech-to-text-supported-languages. Google for Developers. 2022. Machine Learning Crash Course. 2022. https://developers.google.com/machine-learning/crash-course. 2023. Machine Learning Glossary, ML Fundamentals. Google for Developers. 2023. https://developers.google.com/machine-learning/glossary/fundamentals. Gonzalo Brizuela, Roberto, and Eduardo C. Garrido Merchant. 2023. ChatGPT is not all you need. A state-of-the-art review of large generative AI models, AR14. https://doi.org/10.48550/arcs4.2301.04655. Grant, Nico, and Kashmir Hill. 2023. Google's photo app still can't find gorillas. And neither can Apple's. The New York Times, 2023, section. Technology. https://www.newyorktimes.com/2023/05/22/technology/AI-photo-labels-google-apple.html. Griffey, Jason. 2019, Artificial Intelligence and Machine Learning in Libraries. Gwern. 2023, Douglas Hofstadter changes his mind on deep learning and AI risk. https://www.lesrom.com/post/camgddjq2eyqkb5pp/Douglas-Hofstadter changes-his-mind-on-deep-learning-and-AI. 517. Hacking, Ian. 1999, The Social Construction of What? London, Harvard University Press. Pi. 2023, AI Index Report 2023, Artificial Intelligence Index. 2023. https://aiindex.stanford.edu/report/. Hansen, Norwood Russell. 1958, Patterns of Discovery. Cambridge, Cambridge. University Press. Hart, Moritz, Eric Price, and Nathan Srebro. 2016, Equality of Opportunity in Supervised Learning, Preprint, R14. https://doi.org/10.48550/arcs4.1610.024113. Harper, Charlie. 2018, Machine Learning in the Library, or How I Learned to Stop Worrying and Love My Robot Overlords. The Code 4 Live Journal, number 41. https://journal.code4lib.org/articles/13671. Park Rain, Patricia. 2020, featuring the Getty Vocabularies, 91. Harris, Richard. 2002, The de Havilland D.H.82 Tiger Moth and the Moth Family. 2002, https://harris1.net/hold/av/8/8_moth.htm. Hauptmann, Robert. 1988, Ethical Challenges in Librarianship. Oryx. 2002, Ethics and Librarianship. Jefferson, North Carolina, McFarland. Heatley, Louise M., 2023. National Center for Text Mining, NACTM. XHTML. NACTM. 2023, https://www.nactem.ac.uk/index.php. Heaven, Will Douglas. 2022, Why Meta's latest large language model survived only 3 days on mine. MIT Technology Review. 2022. https://www.technologyreview.com/2022/11/1863487/meta-large-language model-AI-only-survived-3-GPT-3-science/. Henderson, Leah. 2020, The Problem of Induction. In the Stanford Encyclopedia of Philosophy, edited by Edward N. DeZalta, Spring 2020. Metaphysics Research Lab. Stanford University. https://plato.stanford.edu/archive/spr2020/entries/induction-problem/. Hernan, Miguel. 2022, Causal Diagrams, Draw Your Assumptions Before Your Conclusions, edX. 2022, https://www.edx.org/course/causal-diagrams-draw-your-assumptions-before-your. Jorland, Berger. 2011, Evidence-Based Practice, an Analysis Based on the Philosophy of Science. Journal of the American Society for Information Science and Technology 62, 1301-10, https://doi.org/10.1002/eci.21523. Hofstadter, Douglas. 2018, The Shallowness of Google Translate. The Atlantic. 2018. https://www.atlantic.com/technology/archive/2018/018/the-shallowness-of-google-translate/5515570/. Hollerith, Herman. 1889, Art of Compiling Statistics. United States U.S. 3957828, filed September 23, 1884, and issued 1889. https://patents.google.com/patent/US 3957828/n. Pond, and A. H. de Marieke M. van Buchem, and Tina Hernandez Bassard. 2022. Picture a data scientist, a call to action for increasing diversity, equity, and inclusion in the age of AI. Journal of the American Medical Informatics Association, Jamia, 2178-81, https://doi.org/10.1093/jamia/ocac156. Hornick, Kurt, Maxwell Stinchcomb, and Halbert White. 1989, Multi-Layer Feed-Forward. Networks are universal approximators. Neural networks 2, 5359-66. https://doi.org/10.1016/08993-6080-89-90020-8. 518. Howard, Jennifer. 2017, What Happened to Google's Effort to Scan Millions of University Library Books. EdSurge News. EdSurge. August 10, 2017. https://www.edsurge.com/news/2017-08-10-what-happened-to-google-s-effort-scan millions-of-university-library-books. Hausen, Colin, and Peter Erbach. 2006, Scientific Reasoning, the Bayesian Approach. 3rd edition, Chicago, Open Court. Juan, Austin, Suraj Subramanian, Jonathan Sum, Khalid Al-Mubarak, and Stella Biederman. 2018, The Annotated Transformer. 2018. http://nlp.cs.harvard.edu/annotated-transformer/. Hugging Face. 2023, Hugging Face, the AI Community Building the Future. 2023. https://huggingface.co. Huntington Klein, Nick. 2022, The Effect, An Introduction to Research Design and Causality. The Effect. https://theeffectbook.net/index.html. Huynh, Chip. 2023, Building LLM Applications for Production. 2023. https://winchip.com/2023/04/11/llm-engineering.html. IFLA. 2012, FLA Code of Ethics for Librarians and Other Information Workers, full version, IFLA. 2012, https://www.ifla.org/publications/ifla-code-of-ethics for-librarians-and-other-information-workers-full-version/. 2020, IFLA Statement on Libraries and Artificial Intelligence. https://repository.iflawd.org/handle/123456789/1646. Imbler, Sabrina. 2021. This moth's name is a slur. Scientists won't use it anymore. The New York Times, 2021, section. Science. https://www.newyorktimes.com/2021/07/09/science/gypsy-moth-romany-entomological-society.html. Iris.ai, 2023. The Workspace Tools. Iris.ai, your researcher workspace. 2023. https://iris.ai/features/ Izquierdo, H. Andres. 2022, 20 Artificial Intelligence and Text and Data Mining. Future Rules for Libraries. In Navigating Copyright for Libraries, edited by Jessica Coates, Victoria Owen, and Susan Riley, 497-540. De Gruyter Soar. https://doi.org/10.15/9783110732009-022. Jakeway, Eileen, Lauren Algie, Lori Allen, Megan Ferreiter, Jamie Mears, Abigail Potter, and Kate Sward. 2020 Machine Learning Plus Library Summit Event. Summary. LC Labs Digital Strategy Directorate. Joe, Boone Seo, and Tinnit Getbrew. 2020 Lessons from Archives, Strategies for Collecting Sociocultural Data in Machine Learning Conference. In proceedings of the 2020 Conference on Fairness, Accountability, and Transparency, 306-16. Fat asterisk. 20. New York, USA, Association for Computing Machinery. https://doi.org/10.1145/3351095.33728229. Johansson, Johanna, Tor Peterson, and Christian Johansson. 2021, Studying Humanto-Computer Bias Transference. AI and Society. https://doi.org/10.1007/00146-021-01328-4. Johnston, Lisa R., and John Jeffries. 2015, Teaching Civil Engineering Data Information. Literacy Skills, an E-Learning Approach. In Data Information Literacy, edited by Lisa R. Johnston and Jake Carlson, 149-78. Librarians, Data, and the Education of a New Generation of Researchers. Purdue University Press. https://www.jstor.org/stable/j.ctt6wq2vh.12. 519. Jurafsky, Dan, and James H. Martin. 2023, Speech and Language Processing. 2023. https://web.stanford.edu/jurafsky/slp3/. Jurafsky, Daniel, and James H. Martin. 2021, Chapter 24 Chatbots and Dialogue. Systems. In Speech and Language Processing. Daniel Jurafsky and James H. Martin. Copyright 2021. All rights reserved. Draft of December 29, 2021. https://web.stanford.edu/jurafsky/slp3/24.pdf. Kahneman, Daniel. 2011, Thinking, Fast and Slow. Penguin Books. Kamrat, Greg. 2023, Data Independent, YouTube. 2023. https://www.youtube.com/channel/ucr2ct3pdoisysych5hko-q. 2023. Learn LangChain. Jupyter Notebook. https://github.com/gcamret/langchain-tutorials. Kaplan, Jared, Sam McCandlish, Tom Hennigan, Tom B. Brown, Benjamin Chess. Rewan Child, Scott Gray, Alec Radford, Jeffrey Wu, and Dario Amade. 2020. Scaling Laws for Neural Language Models, R14. https://doi.org/10.48550/arcs4.2001.08361. Karpathy, Andre. 2023 A.D. A Baby GPT. Reddit post. r/machine learning. www.reddit.com//mckinneylearning/comments/12h1zld/d_a_baby_gpt/. 2023 B. Deep Neural Nets, 33 years ago and 33 years from now. 2023. https://carpathy.github.io/2022/03/14/lacoon198 Philosophy. https://www.gutenberg.org/files/5827/h/5827-h.htm. Rutkowski, Greg. 2023, Greg Rutkoki, Artist. 2023. https://rutkowski.artstation.com. Sada, Tamar. 2015, From Search to Discovery. Bibliothèque Firstjung UND Praxis 39. 212-24. https://doi.org/10.15/bfp-2015-0028. 527. Samuel, Arthur L., 1959. 8-move opening utilizing generalization learning. C. Appendix B, Game G, 43.1 Some studies in machine learning using the game of checkers. IBM Journal, 210-229. In. Sanderson, Grant, and 3 Blue 1 Brown, Directors 2017a. But what is a neural network? Chapter 1, Deep Learning. https://www.youtube.com/watch?v=RCRuvian Directors 2017b. Gradient Descent, How Neural Networks Learn Chapter 2, Deep Learning. https://www.youtube.com/watch?v=IHCWWFWA-W. Sanji, Majida, Hassan Behzadi, and Jisoo Gamroki. 2022, Chatbot, an intelligent tool. For libraries. Library high-tech news ahead of print. https://doi.org/10.1108/lhtn-01-2021-0002. Saravia, Elvis. 2023, Prompt Engineering Guide, Nextra. 2023. https://www.promptingguide.ai. Shines, Richard. 1997, An Introduction to Causal Inference. In Causality and Crisis. 185-200. University of Notre Dame. Schlicht, Matt, and Ben Parr. 2023, Chatbots Magazine, the #1 place to learn about chatbots. Chatbots Magazine. 2023, https://chatbotsmagazine.com. Sebastian, Jacob, Eugene Su, and Sylvester O. Orame. 2017, Emerging Approaches in Literature-Based Discovery, Techniques and Performance. Review. The Knowledge Engineering Review 32, E12. https://doi.org/10.101768889170000042. Seth, Ari, Dar 2023. How ChatGPT is Trained. https://www.youtube.com/watch?v=bprsbzxcavu. Shannon, C.E., 1948. A Mathematical Theory of Communication. The Bell System. Technical Journal 27:379 for 23, 623-56. Shannon, Claude Elwood, and Warren Weaver. 1949, The Mathematical Theory of Communication. Urbana, University of Illinois Press. Single, Amit. 2012, Introducing the Knowledge Graph, Things, Not Strings. Google. 2012, https://blog.google/products/search/introducing-knowledge-graph-things-not/. Smallheiser, Neil R., 2017. Rediscovering Don Swanson, The Past, Present and Future of Literature-Based Discovery. Journal of Data and Information Science. Warsaw, Poland, 2, 443-64. https://doi.org/10.15/JDS-2017-0019. Smith, Linda C., 1981. Citation Analysis. Library Trends 30:83-106. Smith, Martha Montague. 1997, Information Ethics. In Annual Review of Information. Science and Technology, 32:339-66. Snow, Karen. 2017, Defining, Assessing, and Rethinking Quality Cataloging. Cataloging and Classification Quarterly 55, 7-8 438-55. https://doi.org/10.1080/0163937.2017.1350774. Society of American Archivists. 2020, SAA Core Values Statement and Code of Ethics. Society of American Archivists. 2020. https://www.archivists.org/statement/saa-core-values-statement-and-code of-ethics. Summers, James. 2017, Torching the Modern-Day Library of Alexandria. The Atlantic. 2017, https://www.theatlantic.com/technology/archive/2017/04/the-tragedy-of google-books/5233320/. Spivak, Nova, and Nick Slavin. 2023, Arch Mission Foundation. Arch Mission. 2023. https://archmission.org. 528. Stamp, Mark. 2017, A Revealing Introduction to Hidden Markov Models. In Introduction to Machine Learning with Applications in Information Security, by Mark Stamp, First Edition, 7-35. Chapman and Hall/CRC. https://doi.org/10.1201/97813152132132622-2. Stanford HI. 2023 AI will transform teaching and learning. Let's get it right. Stanford HI. 2023. https://hai.stanford.edu/news/ai-will-transform-teaching and learning-let's-get-it-right. 2023b Generative AI, Perspectives from Stanford HI. 2023. https://hai.stanford.edu/site/default/files/2023-03-03/perspectives.pdf. Starmer, Josh, DAR 2020. Neural Networks PT2, Bat Propagation Main Ideas. https://www.youtube.com/watch?the=in2xmbhilt4. Starmer, Josh, and StatQuest, Directors 2019. Gradient Descent, Step by Step. https://www.youtube.com/watch?SDV4F4S2SB8. Strevens, Michael. 2013, Looking into the Black Box. Opinionator. 2013. https://archive.newyorktimes.com/opinionator.blogs.newyorktimes.com/2013/11/24/looking. G into the Black Box/ Suber, Peter. 1999, Paternalism. 1999. https://dash.harvard.edu/bitstream/handle/1/47250117/suber_paternal.htm. Suarez, Jorge. 2021, Continuous Offline Handwriting Recognition Using Deep Learning Models, AR14. https://doi.org/10.485550/arcs4.2112.13328. Solmont, Elizabeth, Elizabeth Petitzes, and Jeremy R. Cooperstock. 2019, Can You Teach Me to Machine Learn? In Proceedings of the 50th ACN Technical Symposium on Computer Science Education, 948-54. 619. New York. New York, USA, Association for Computing Machinery. https://doi.org/10.1145/3287324.3287392. Suresh, Harini, and John Guttag. 2021, A Framework for Understanding Sources of Harm Throughout the Machine Learning Life Cycle. Inequity and Access in Algorithms, Mechanisms, and Optimization, 1-9. New York, USA, ACM. https://doi.org/10.1145/3465416.3483305. Suits Kever, Ilya, Oriol Vinyals, and Kwok V. Lu. 2014, Sequence-to-Sequence Learning with Neural Networks. In Advances in Neural Information Processing Systems. Volume 27. Curran Associates Incorporated. https://proceedings.neurips.cc/papers/2014/hash/14AC554F27472C5D894EC1C3. C743D2 abstract.html. Sutton, Richard S., and Andrew G. Bartow. 2018, Reinforcement Learning, an Introduction. Second edition http://incompleteideas.net/book/the-book-2end.html. Svenonius, Elaine. 1969, Review of Two Kinds of Power, An Essay on Bibliographical Control by Patrick Wilson. The Library Quarterly, Information. Community, Policy 39, 112-14, http://www.jstor.org/stable/4305960. 2003, Design of Controlled Vocabularies. In Encyclopedia of Library End. Information Science, 822-38. New York, Marcel Decker. Swanson, D.R., 1986. Undiscovered Public Knowledge. Library Quarterly 56:10318. Tate, Elizabeth, and Cameron M. Pearson. 2022, Artificial Intelligence and Robots in Libraries, Opportunities in LIS Curriculum for Preparing the Librarians of Tomorrow. Journal of the Australian Library and Information Association 71. 256-74, https://doi.org/10.1080/108.2022.20811111. 529. Tashia, Jason. 2017, Courts are using AI to sentence criminals. That must stop now. Wired, 2017, https://www.wired.com/2017/04/courts-using-AI-sentence criminals-must-stop-now/. Tay, Baron. 2022, List of Innovative Literature Mapping Tools. Aaron Tay's Musings. About Librarianship. 2022. https://musings-about-librarianship.blogspot.com/p/list-of-innovative-literature-mapping.html??classic. Taylor, Arlene G. 2004. The Organization of Information. 2nd edition, Westport, Connecticut. Libraries Unlimited. Taylor, Ross, Marchand Cardis, Gilliam Cucurell, Thomas Silem, Anthony Hartshorn. Alvis Saravia, Andrew Poulton, Victor Kirkes, and Robert Stojnik. 2022. Galactica, a large language model for science, AR-14. https://doi.org/10.48550/arcs4.2211.09085. Taylor, Wilson L., 1953. Close Procedure, a new tool for measuring readability. Journalism Quarterly 30, 415-33. https://doi.org/10.177/10776990530300004001. Teixeira, Lawrence. 2023, The New Open AI GPT-4 Vision on ChatGPT, Bridging the Gap Between Text and Image Understanding. 2023. https://medium.com/@Lawrence-Teixeira/The New Open AI GPT Vision on ChatGPT, Bridging the Gap Between Text and Image Understanding at CA6. Tela, Adiyinka. 2020, Robots are coming to the libraries. Are librarians ready to accommodate them? Library High-Tech News 37, 813-17. https://doi.org/10.1108/LHTN-05-2020-0047. Tela, Adiyinka, and Yusufaya Dejiajani. 2022, Robots and Public Libraries. Library High-Tech News 39, 715-18. https://doi.org/10.1108/LHTN-05-2022-0072. Tenney, Ian, Patrick Xia, Berlin Chen, Alex Wan, Adam Poliak, R. Thomas McCoy. Najum Kim, et al. 2022. What do you learn from context? Probing 4. Sentence structure in contextualized word representations. In https://openreview.net/forum?id=SJZSGNRCKX. The AI Advantage, DAR 2023, 100 plus insane ChatGPT vision use cases. https://www.youtube.com/watch?v=YWNNRZC7-T0. Thalakkaratan, Menashe, Katrina Faulkner, and thus Hari Adapatu. 2020, a systematic review on literature-based discovery, general overview, methodology, and statistical analysis. ACM Computing Surveys 52, 61-34. https://doi.org/10.1145/3365756. Thoppelen, Romal, Daniel de Freitas, Jamie Hall, Noam Shazir, Upworth Kolshrestha. Penza Cheng, Alicia Jean, et al. 2022. Lambda, Language Models for Dialogue. Applications, AR14. https://doi.org/10.48550/arcs4.2201.08239. Thunstrom, Almira Osmanovic. 2022, we asked GPT-3 to write an academic paper about itself and then we tried to get it published. Scientific American. 2022, https://www.scientificamerican.com/article/we-asked-gpt-3-to-write-an-academic paper about-itself-then-we-tried-to-get-it-published. Turner, Ash. 2018, how many people have smartphones worldwide? October 2022. 2018, https://www.bankmycell.com/blog/how-many-phones-are-in-the-world. Tversky, A. 1974. Judgments Under Uncertainty, Heuristics and Biases. Science. 185:1124-1131. 530. Tversky, Amos, and Daniel Kahneman. 1982, Evidential Impact of Base Rates. In Judgment Under Uncertainty, Heuristics and Biases, edited by Daniel Kahneman, a Slavic, and Amos Tversky. Cambridge University Press. UCL. 2018, Transcribe Bentham. Bentham Project. 2018. https://www.ucl.ac.uk/bentham-project/transcribe-bentham. UCSF Office of Diversity and Outreach UCSF. 2022, Unconscious Bias Training. University of California, Office of Diversity and Outreach. 2022. https://diversity.ucsf.edu/programs-resources/training/unconscious-bias-training. ujet.cx 2022a. Critical State of Automation in Customer Experience. UJET. 2022. https://ujet.cx/resources/reports/critical-state-of-automation-customer experience-2022-report-LP. 2022b, UJET research reveals chatbots increase frustration for 80% of consumers. UJET. 2022. https://ujet.cx/press-releases/ujet-research- reveals chatbots-increased- frustration. University of Alberta Library. 2023, Evidence-Based Library and Information Practice. 2023, https://journals.library.ualberta.ca/eblit/index.php/ablit. Uskerite, Jacob. 2017, Transformer, a novel neural network architecture for language understanding. 2017. https://ai.googleblaw.com/2017/08/transformer-novel-neural-network.html. Vanderweel, Tyler J., and Nancy Stott. 2011, Causal Diagrams for Empirical Legal Research, a methodology for identifying causation, avoiding bias, and interpreting results. Law, Probability and Risk, a Journal of Reasoning under Uncertainty 10, for 329-54, https://doi.org/10.1093/lpr/manager019. Veswani, Ashish, Noam Shazir, Nikki Palmer, Jacob Uskerite, Lion Jones, Aidan N. Gomez, Lukash Kaiser, and Ilya Palasukin. 2017, Attention is All You Need. AR14. https://doi.org/10.48550/arcs4.1706.03762. Vince, Joseph. 2017, Virtual Reference Librarians, Chatbots. Library High-Tech News. 34, 4528, https://doi.org/10.8/lht-03-2017-0016. Vaughn Hilgers, Philip, and Amy M. Laneville. 2006, The 5 Greatest Applications of Markov Chains. 2006, http://langvilla.people.cofc.edu/mcat7.pdf. W3C Working Group. 2014, RDF 1.1 Primer. 2014, https://www.w3.org/tr/rdf11- primer/. 1. Angelina, Solon Barocas, Kristen Laird, and Hannah Wallach. 2022, Measuring Representational Harms in Image Captioning. In 2022 ACM Conference on Fairness, Accountability, and Transparency, 324-35. FACCT 22. New York, New York. USA, Association for Computing Machinery. https://doi.org/10.1145/3533146.3533099. Wattenberg, Martin, Fernanda Viegas, and Moritz Hart. 2022, Attack Discrimination with Smarter Machine Learning. 2022. https://research.google.com/bigpicture/attacking-discrimination-in-ml/. Wei, Jason, Shuaji Wang, Dale Shermans, Martin Bosma, Brian Ichter, Fei Xia, ed. Chi, Kwok Lo, and Denis Zhou. 2023, Chain of Thought Prompting Elicits Reasoning in Large Language Models, AR14. https://doi.org/10.48550/arcs4.2201.11903. 531. Wei and Denis Zhou. 2022, Language Models Perform Reasoning via Chain of Thought. 2022, https://ai.googleblaw.com/2022/05/language-models-perform reasoning-via.html. Weidinger, Laura, Jonathan Wesato, Marybeth Rao, Connor Griffin, Pasen Huang. John Miller, Amelia Glees, et al. 2022. Taxonomy of risks posed by language. Models. In 2022 ACN Conference on Fairness, Accountability, and Transparency, 214-29. FACCT 22. New York, New York, USA, Association for Computing Machinery. https://doi.org/10.1145/3531146.3533088. Weigert, Farina. 2020, Chatbots in Libraries, Library Services. 2020. https://libraryservices.jiscinvolved.org/wp/2020/09/chatbots-in-library/. Weizenbaum, Joseph. 1966, DELIZA, a computer program for the study of natural language communication between man and machine. Communications of the ACM 9, 136-45, https://doi.org/10.1145/3651553.365168. Wells, David. 2021, Online Public Access Catalogs and Library Discovery Systems. Text. 2021, https://www.isgo.org/cyclo/OPEC #6. Winar, Leaf. 2021, Rights. In the Stanford Encyclopedia of Philosophy, edited by Edward N. Zelta, Spring 2021. Metaphysics Research Lab, Stanford University. https://plato.stanford.edu/archive/spr2021/entries/rights/. Wheatley, Amanda, and Sandy Herview. 2019, Artificial Intelligence in Academic Libraries, an Environmental Scan. Information Services and Use 39, for 347-56. https://doi.org/10.3233/ISU-190065. Vidyasari, Adhika Pramana, Supriyati Rustad, Gaurav Fajar Shiddak, Eddie Norsasanko. Abdul Sukar, Afandi, and Rosal Ignatius Moses Sidiati. 2020. Review of Automatic Text Summarization Techniques and Methods. Journal of King Saud University, Computer and Information Sciences. https://doi.org/10.16/j.jksuci.2020.05.006. Wikipedia. 2022a Algorithm. In Wikipedia. https://en.wikipedia.org/w/index.php?title =algorithm. 2022b Algorithmic Bias. In Wikipedia. https://en.wikipedia.org/w/index.php?title =algorithmic _bias. 2022c Artificial Linguistic Internet Computer Entity. In Wikipedia. https://en.wikipedia.org/w/index.php?artificial_linguistic_internet_com. Peter_entity and olded equals 1112755868. 2022d False Positives and False Negatives. In Wikipedia. https://en.wikipedia.org/w/index.php?title =false_positives_and_false_negative. ES and olded equals 1088158900. 2022 E Lambda. In Wikipedia. https://en.wikipedia.org/w/index.php ? Lambda & old ID =11038326671. 2022 F. Vatican Apostolic Archive. In Wikipedia. https://en.wikipedia.org/w/index.php ? Title Vatican_Apostolic_Archive & old ID = 10955410005. 2023 A. CAPTCHA. In Wikipedia. https://en.wikipedia.org/w/index.php ? Title CAPTCHA. 2023 B. Confirmation bias. In Wikipedia. https://en.wikipedia.org/w/index.php ? Title confirmation_bias &old ID =1186068. 624. 532. 2023 C. Crowdsourcing. In Wikipedia. https://en.wikipedia.org/w/index.php ? Title crowdsourcing & old ID =11318788886. 2023 D. Evidence-based practice. In Wikipedia. https://en.wikipedia.org/w/index.php ? Title evidence-based_practice & old ID =11417977027. 2023 E. Explainable artificial intelligence. In Wikipedia. https://en.wikipedia.org/w/index.php ? Title explainable_artificial_intelligence and olded =11441127716. 2023 F. Google Hummingbird. In Wikipedia. https://en.wikipedia.org/w/index.php ? Title Google_Hummingbird & old ID =1152805,833. 2023 G. Lane chain. In Wikipedia. https://en.wikipedia.org/w/index.php ? Title lane chain. 2023 H. Liberty leading the people. In Wikipedia. https://en.wikipedia.org/w/index.php ? Title liberty_leading_the_people & old ID =11589011762. 2023 ith Library. In Wikipedia. https://en.wikipedia.org/w/index.php ? Title library & old ID =11406010084. 2023 J. Literature-based discovery. In Wikipedia. https://en.wikipedia.org/w/index.php ? Title literature-based_discovery & old ID =11409272264. 2023 K. Open Archives Initiative Protocol for Metadata Harvesting. In Wikipedia. https://en.wikipedia.org/w/index.php ? Title open_archives_initiative_protocol _for_metadata_harvesting and olded =11333357880. 2023 L. PageRank. In Wikipedia. https://en.wikipedia.org/w/index.php title =pager8 old ID =11654483888 2023 Rank Brain in Wikipedia. https://en.wikipedia.org/w/index.php title =rankbrain old ID =11400340006 2023 Tay chatbot in Wikipedia. https://n.wikipedia.org/withindex.php title =Tay_chatbot 2023 The Library of Babel in Wikipedia. https://en.wikipedia.org/w/index.php title =library_of_babel old ID =1141 372,445 2023 Wikipedia Artificial Intelligence in Wikipedia. https://en.wikipedia.org/w/index.php title Wikipedia:\artificial_intelligence_ol did =115771416 2024 her in Wikipedia. https://n.wikipedia.org/withindex.php title =film and old it =12379111810 Wilburn, Brad. 1999 Spice for the Good Life. Issues in Ethics 10. Wilson, P. 1968. Two Kinds of Power, an essay on bibliographical control. Berkeley. University of California Press. Wolf, Matt, 2023. Future Tools, find the exact AI tool for your needs. 2023. https://www.futuritools.io. Wolford, Ben. 2018, What is GDPR, the EU's new data protection law? GDPR.eu. 2018, https://gdpr.eu/what-is-GDPR/ 533. Wolfram. 2023 A. Wolfram Mathematica, Modern Technical Computing. 2023. https://www.wolfram.com/mathematica/. Wolfram, Stephen. 2023 B. ChatGPT gets its Wolfram superpowers. 2023. https://writings.stephenwolfram.com/2023/03/chatgpt-gets-its-wolfram superpowers/ Wolkoff, K. N. 1996. The Problem of Holocaust Denial Literature in Libraries. Library. Trends 45:87, 96. Wood, Barbara, and David Evans. 2018, Librarians' Perceptions of Artificial Intelligence and Its Potential Impact on the Profession. Computers in Libraries. 38, 1. https://www.researchgate.net/publication/322977069_librarian_perceptions _of_artificial_intelligence_n_its_potential_impact_on_the profession. Writer, Beta. 2019, Lithium-ion batteries. https://link.springer.com/book/10.007/978-3-030-16800-1. Sion, Chloe. 2023, OpenAI's GPT-4 is closed source and shrouded in secrecy. Vice. 2023. https://www.vice.com/and/article/ak3w5/openace-gpt-4- is-closed-source and-shrouded-in-secrecy. Su, Bin Phone, Ziwan Peng, Bowen Lei, Sababrata Mukherjee, Yichen Lu, and Dongguan Su. 2023. ReWO, Decoupling Reasoning from Observations for Efficient Augmented Language Models, AR14. https://doi.org/10.48550/arcs4.230518323. Yang, Jinyuan, Lin Jieli, Kevin Lin, Jianfeng Wan, Chengqing Lin, Zicheng Lu, and Lijuan Wan. 2023. The Dawn of LMMs, Preliminary Explorations with GPT-4v, Ishan, DAR 14. https://doi.org/10.48550/arcs4.2309.17421. Zellers, Rowan, Ari Holtzman, Yonatan Bisk, Ali Farhadi, and Yejin Choi. 2019. Hella swag, can a machine really finish your sentence? AR14. http://arcs4.org/abs/1905.07830. Zhang, Marcia Lei. 2005. Construction of Controlled Vocabularies, a Primer, based on Z39.19, 2005. Zhu, Adam. 2023. Solving a Machine Learning Mystery. MIT News, Massachusetts. Institute of Technology. 2023. https://news.mit.edu/2023/large-language-models-in-context-learning-0207. Zheng, Lianmin, Weilin Chang, Ying Sheng, Siyuan Xuan, Zhanhao Wu, Yonghao Zhuang, Zi Lin, et al. 2023. Judging LLM as a Judge with MT Bench and Chatbot Arena, AR14. https://doi.org/10.48550/arcs4.23060.05685. Ziegler, S.L., 2019. Digitization Selection Criteria as Anti-Racist Action. The Code for Lib. Journal, number 45. https://journal.codeforlib.org/articles/14667.